department to kindly felicitate him as a token of our respect and gratitude by presenting a shawl, a memento, and a plant. Kotnala sir and Dr. Gore sir are requested to please come forward on the dais. Sir, stage पे आ जाओ, stage में ऐसे ही आ जाओ. Please everyone give a big round of applause. We are presenting a token of appreciation to Professor R.K. Kotnala sir by presenting him a shawl, a memento, a plant having shatavari, and a conference kit as a gesture of our appreciation and warm regards. Please everyone give a big round of applause. Now, it is my privilege to introduce our keynote speaker, Professor R.K. Kotnala sir, founder of NSCI Delhi. Professor Kotnala is a globally renowned scientist with over 36 years of rich experience in the fields of sustainable energy, green hydrogen, nanoscience, and advanced functional materials. He has been associated with CSIR National Physical Laboratory, where he served as Chief Scientist and Head of the Environmental Sciences and Biomedical Metrology Division. With an outstanding academic record, he has contributed more than 586 research publications, received over 18,000 citations, and holds an H index of 66. He also holds several US and Indian patents, reflecting his significant contribution to scientific innovation. Please everyone give a big round of applause. Also, he is widely recognized for his pioneering invention of the hydroelectric cell, a revolutionary technology for clean electricity and green hydrogen generation through water splitting at room temperature. Among his many honors, he is a recipient of the Renewable Energy India Award 2018 and the Gold Award at the India Smart Gold Forum 2025 with his exceptional contributions to green energy technologies. Today, he will be delivering his keynote talk on enhancing hydrogen generation by reducing hydrogen binding energy in SNO2 hydroelectric cell with Fe doping. I now humbly invite you, sir, to kindly address the gathering and share your valuable insights. Over to you, sir. I request Professor Kotnala, sir, to come on the dais and present his keynote address. Please, everyone, give a big round of applause for Professor Kotnala, sir.
Thank you, Dr. Verma, for a concise introduction. And I am really thankful to the principal of the Shivaji College, Dr. Bharadwaj, and then the person who have been in the physics department. The whole faculty has been working for months together to organize this, in which the lead was definitely from the Dr. Shiv Shankar Gaur, who had been, running after it, and with him always the Dr. Ravinder Singh. They worked so hard to organize a very important conference, which is a international, that too in a Shivaji college for the first time. And I really congratulate not only to them, but also to the students who are here, present over here, and would like to listen. And out of this, Dr. Mahesh Sharma from the CSIR, he is one of the very senior most scientists. He is also sitting, who had been my colleague also. And it's a good chance that we can at least talk about my work, hydroelectric cell. It's not only my one of the student, Dr. Jyoti. So I would like to just begin with it. If you look at the title, Enhancing Hydrogen Generation by Reducing Hydrogen Binding Energy in SNO2 hydroelectric cell with Fe3 plus doping. Now the question is that why SNO2 and what is hydroelectric cell? So hydroelectric cell is the India's pride. It is for the first time after the 110 years after Sir C.V. Raman, we could come out with such a revolutionary work as an energy device. And that hydroelectric cell, it has been coined by me, my student, and the work completely is done in terms of the raw materials for the hydroelectric cell. It's a simply nanomaterial, oxygen deficient, and we started with the magnesium ferrite, and today we have got more than 36 compounds on which you can see the hydroelectric cell effect. What the hydroelectric cell is really, it's an interdisciplinary device. It's not based only on the physics, but it is based on even the nanoscience as well as the electrochemistry and material property, that any of the material, if you are synthesizing in the lab and if you make it a oxygen deficient and nanoporous, what is happening? The water, whenever it comes in touch with this material, it immediately splits the water molecule into H plus and OH ion. Mostly H plus ion cannot travel alone. So the hydronium ion, H3O plus ion is there, which will migrate, travel, and the OH ion. So for that, how to collect? So as a physicist, I have got a very long experience in silicon solar cell. You may not be aware that I have done my PhD. I am the first PhD in India on silicon solar cell. And I was working for last 18 years on it, and I was pushing it all the different boundaries, but could not push the boundaries of the science to that level. Particularly solar cell is a PN junction. It's a basically P plus NN plus junction. That is the only one based on the silicon. So today whatever we see the solar panel, so that is the only one that. So based on silicon. But because of the limitation of the country, what we were not having those much facilities to work on the semiconductor devices. Of course I had created, but those are very simple. It cannot go for the long. If you have to go run for the science, then all over the world the work was being done, even the molecular beam epitaxial layers. So we were not having that time in India, any of the MBE. It was a very expensive, and it was not being also sold to the India. So I moved towards the magnetic materials, and around 2000 year, nanomaterial I was working with, and then within the 2-3 years we realized that oxygen deficient material can really split the water molecule, but in a very small quantity. The current that time was in picoampere. So it was a really challenge, because I was a solar cell person, so I know that we need a milliampere, hundreds of the milliampere, not the 1 milliampere, 2 milliampere. So we kept on working, and since 2002 onwards, worked on how to make our material more efficient for water splitting. So that we could go for the oxygen efficiency more in the magnesium ferrite and as well as the nano porosity. Nanopores we created around 30% in the material. It was not easy. But these nanopores were responsibly finally to dissociate water molecule by developing a very high electric field. But the challenge was that if it is dissociating the water molecule, which we are calling as a water splitting, how to separate those ions and then collect. So the only answer was p-n junction, because I was aware of the p-n junction but could not be done much into it. We were finding the current from picoampere to nanoampere. So we moved towards the electrochemistry. So we use the two electrode because the chemistry is the another one which can really collect the ions, separate the ions. So we made it a cell structure on the material palette and on the two sides of the palette, one face as a zinc electrode, other face as a silver electrode. And migration of our all these ions, OH ion was going towards the zinc side and forming the zinc hydroxide, releasing two electrons. Those two electrons move towards the another cathode, silver cathode, put on this. I'll show you in this next, because I am giving you a just brief that how is it. So then you get the immediately collected over there the two electrons from the zinc hydroxide from the anode goes towards the cathode, and their H plus ion have already migrated because of the electrode potential of our silver. So once those have been migrated, that means then the H plus ion have been turned into the H and finally hydrogen. So what has happened, that producing by hydroelectric cell is not only the current but a voltage also. So the voltage is 0.98 volt, and the current at that time we were getting in microampere initially, then from microampere we moved towards the milliampere, and today we get in hundreds of the milliampere in the small cell. So that is the journey which had been there, and Dr. Jyoti Saha was doing her PhD program in the humidity sensing of the material, and she could publish a lot of good papers, and then we continued in that journey, and even today we are doing it. But the problem is, because all the raw materials which we are using are from India. Today even we have to go for a solar cell, or we talk about the silicon chip microprocessor, we have to buy silicon single crystal from abroad. We are not producing, and if someone is producing, then the foreign company is here and producing and giving you. The problem with this hydroelectric cell was only one thing, that everything should be in nation. So we coined the name. Material is in India, we are abundant, iron oxide, magnesium carbonate, lithium carbonate. So that was a start, and we could publish the first paper in 2016 on International Journal of Research, which is a Wiley publication, with a great difficulty because no one was accepting that it is something big. But that was the time in 2016. If we send any paper within the 30 days, within 18, 21 days, any of the journal which has got an impact factor of 8 or 10, they accept it. So that's the scenario. It has been changed, and within the, I'll say the last 6 years, 154 papers have been published in the journal. More than that is there, but which are in our own, because not only from India as a group, Indian Institute of Science, IITs, Delhi University, all have been working. Whether you talk about DTU, name any of the good institution, they are working on it. In the abroad, IOP, Brazil, then again recently from the Spain, one paper have been published theoretically on this by a very senior professor, that how the hydroxyl is working and what should be the possible another theory, another direction to it. And not only to that, ETH Zurich is also working on the water splitting. There is one group. They also work on this because they are working in the different direction. So we have got a very different kind of a, recognitions, honors on this hydroelectric cell. And most important is, today, as I have said, we more than 36 compounds, whether you make it a composite, you make it an oxide, you take any oxide. So any oxide, when you talk about TiO2, SiO2, Al2O3, and SNO2 also, not only oxide, then you make a multiferrite composites, then you make another kind of the composites. So there is a lot being done, and all solar cell work we are following from the abroad, not only on that, other materials also. But once hydroelectric cell has come, then they all have to follow us. So we have got a citation around 400 in the one paper within the last 6 years on the hydroelectric cell. Of course, from India, whatever you publish, they have a doubt, one question mark, whether it's a good or not. But you can imagine that if within the 6 years you can get a 400 citations, 200 citations on those papers. Besides that, I have got the other papers also, which are in the different directions, where I have set the other kinds of the milestones which are globally known. But we are working only on hydrocell. I stopped working for last 10 years, rather than 10, maybe more. Only because I'll not work on only any of the material except for the hydroelectric cell. So this is the dedication, and when I could not find a funding on this, so we have started with our new institute with self-funding, New Science Creators Institute. It's you can see here. Anyway, it will not read. So they say, there you can see, and we are sending it in this institute. Our idea is to go for the pilot plant for the production as a product from the hydroelectric cell. So that's our intention moving ahead. But this title, which you will see, is based on green hydrogen. So once it is based on green hydrogen, so it is only one device which works on dual technologies. It produces current in the one direction, current and voltage, so it is acting as a green electricity source by just putting water. We are not putting any acid, anything on it. Then the other one is producing the hydrogen. So production of hydrogen is done in different mode. So that also paper we have published in International Journal of Hydrogen Energy, that way back in 2018. So you can imagine that as soon as the first invention had been how to accelerate the water splitting by external energy. In the hydroelectric cell, when we are generating the electricity, we are not taking any energy from outside. But for hydrogen, I thought that time, why not to work in this direction? It is to be taken as a green hydrogen. Today you all know that we talk about the hydrogen, green hydrogen. It's rather I'll say the buzzword for anything after the solar cell. So why the green hydrogen? You all know, if the LPG you are using as a cooking, so for the cooking we have already put we are working on the project that for the cooking gas we are going to work on hydrogen production by the hydroelectric cell. So these things matter a lot, that when you feel that what you can do, how it is to be done, what is to be done. Here I have shown to this, and even the hydrogen production, if I say, for last 3 years we are working more towards the hydrogen production. Electricity generation is already at a level what the solar cell is delivering. The solar cell is a very long history of 85 years. Whatever the current and voltage as a power output it gives for the solar cell, that we already crossed, means per centimeter square, which is a normally 35 milliampere, 37 milliampere per centimeter square. But we are getting 45 milliampere per centimeter square, and the voltage is 0.98 volt, and for the solar cell it is only 0.6 volt. So whenever the power output you talk, you multiply V into I. Once we have already passed that for the electricity generation beyond our solar cell, silicon solar cell, now for the hydrogen. You all may be knowing that all over the world, even India is struggling hard, buying the electrolyzer from the Linde. Linde group is from Germany. They are the master for more than 100 years on liquid nitrogen plants and liquid helium plants. So they started working 10 years before on your hydrogen generation. But the green hydrogen is a different concept. There you need a different thing, but they are mixing it fine. But in our case, we are getting the green hydrogen, that to 99.98% purity level, which we have already published. We have got the US patent, we have got the regular Indian patent on them, and so many papers we are publishing only at the moment on hydroelectric cell. So that is the, we have already taken a total mission how to work on it only for hydroelectric cell. So once I talk about this SNO2 here, in the electrolyzer, we have already crossed the limit. Because if you may be knowing or may not, I'll just give you the information that green hydrogen, when it's to be produced, so all over the world, they say 55 to 60 kilowatt hour is being used in electrolyzer, and that electrolyzer is nothing but a improved fuel cell. So you can imagine how much expensive is the fuel cell. So that is the state, and that's a 55 to 60 kilowatt hour for 1 kg hydrogen to produce. And we have already worked in our lab where we are not doing so much, but we do definitely make it a 0.2 kg in the lab. And then as we go for the production, then it will be the bigger cells, and where we can get the hydrogen for not the 55 and 60 kilowatt hour, but we have worked and we have moved to a 45 kilowatt per hour based on the hydroelectric cell. So one can imagine that even as an electrolyzer, it's beating, means the records are beyond that. And most important, it's a very cheap, because all raw materials are cheap, all is in India, and everything is done in India. So on the both front we are working very well, but definitely we work so I'll say so long hours every day, every week, every month, and here are the different groups who are working in India, and particularly in Shivaji College, these two people, Dr. Ravinder and Dr. God, also working in that direction, that how to move this mission in a better way. So it's not only one group, around maybe 40 groups, India and abroad. They are working on this. And when we come to the next one, if you look at in the history, how from the Volta cell, which is in 1800 years before, and with the time, you can see the Lake-Lanchi cell, other cell which have been there, then solar cell and hydroelectric cell is there on the just recent in 20. But there is a gap of 50 years to coming something new into this direction. So hydroelectric cell, how important it is. The storage batteries we have kept aside because all these are primary cells, Volta cell, Leclanchi cell, and even the hydroelectric cell and solar cell also, because when the light falls on it, one photon generates the electron hole pair, and that generates the electricity. So, but we have moved so high, that's the specialty of it. You can see the just a schematic diagram of the hydroelectric cell, which is a brown in color on the left side, and brown color, silver is a white, it's a cathode. On the back side, it's a zinc fine sheet we have put, I'll call it a zinc foil, and then we get a, today, for the 3 by 3 inch square, because that also we do in the lab. So we have scaled up our size from the very small sample. You know that how in the lab, how much small samples are being created, but 3 by 3 inch, we have got 723 milliampere in that, 0.72 ampere. And voltage is 0.98 volts, so you can consider it to be 1 volt. So it's a 0.7 watt in simple watts for 3 by 3 inch. We have to go make this journey. We are making, even fabricating in the lab, 4 by 4 inch also. But we have not optimized it yet. We are optimizing it. There the current will further increase. It will go beyond the watts. So within a short period, because our concept is that we must bring it to the public use. So anything which is, we do in the lab, it takes a very long time to come to the public. So here we have taken another mission, another effort, that how it can be put into this side. The other side has been shown in the lab, a small box enclosure in which we have inserted the, you can see the few cells, hydroelectric cell 3 by 3 inch, and connected from the outside, and we are applying the low voltage and the low current, and then we get a green hydrogen, because whatever we want to publish, we have to show you that the what kind of this one. Everything is available in our lab. It's open to all, because lot of people come, industry people come, and students come, faculty come, and they observe that what we are doing. It's not that, because it is open. We are not keeping such a secret, but definitely fabrication of the material, in the material, how we are processing, because it's a simple one. In any of the college or even at your garage, you can prepare the hydroelectric cell. Because what you have to do, it's a simple solid state technique, mix magnesium carbonate, iron carbonate, or in this case SNO2 only, right, tin oxide. So any oxide, you mix them, sinter, the pre-sintering you do it, which is normally calcination we call, around 800 degrees C. Then after that you take out that powder, you grind it and then put it in a pellet form or the cylinder form. We have worked on the different types of the hydroelectric cell, and what we are getting into it, that's you have to sinter it at around 1050 degrees C. You get the hydroelectric cell. So you need a furnace, you need a grinding. You can do it by even pestle mortar, or we have got the ball mills also, because once we are going to take a bigger size, so we are doing that. So that all, and it is filled with the water, and hydrogen is being, okay. There is actual pictures also. This is the award already.
You do the coatings?
Pardon?
Making the powder, you do the coatings?
No, not coating, pellet.
Oh, you use the pellet?
Pellet. It's approximately between 1 and 2 mm thick pellet, and size is 1 by 1 inch, 2 by 2 inch, 3 by 3 inch.
Can you print it also?
See, whenever we talk about that, you may be knowing that the solar cell is being used, and I had a very long experience in that. There had been trials on the painting, the thin films, but those are not as successful as the solid silicon is being used. Solid silicon means in the crystalline form, then solar cells are made on this. Once the coating is there, then the power output is less, power density decreases, and there are the other problems for coating on that. And here you need the PN junction. There in an organic solar cell, there was a lot of work was being done in 25 years before, and within 15 years it was wind up that it is not possible to have a commercial one with the even thick coating. In the hydroelectric cell, we are not trying because we have that kind of experience is open. So we don't have that much big team and even the funds to work on it. But we know it because it is going to give us a lesser one. It can be for a specific applications. So that's a different criteria. And we being a basically researcher, so what we are doing it, we are doing for the new element, new compound, so that we get some better output and doing it better and better. The value I am giving you, because when I was working in the solar cell, way back in 1985, I was working on the silicon solar cell. We took 8 years to make a solar cell from 15 mm dia circular to 2-inch dia cell. And that too was to be optimized. So optimization took another 2-3 years. And that time I had a very big group in National Physical Laboratory, right? So even though there are the different constraints when you increase the size of the cell, or you go to the thin film, I have a lot of good facility, but when we know that it is in terms of the output energy source, so then you cannot think of the very, very small, the coating that, and anybody can try, I don't mind, but in a market you have to look at what is required and what is not required. So we are working again on it, how to improve our, let's say for 3 years we were working, while earlier we were having the hydrogen. The hydrogen what we are getting, that was 112 kilowatt hour. Because we estimated from that, we are doing the experiment, and then 112 kilowatt hour. We worked on it, same material, same cell, but it is to be put into a different shape, different form. And today, as I have already told, we have gone to 45 kilowatt hour, bringing the power so low. Because the power applied on the electrolyzer is producing the hydrogen for 1 kg. And that too green hydrogen, high purity. So these are the different challenges which one has to learn with the understanding. But this is here one can see that the New Energy Award was given to us immediately in 2018. There Dr. Jyoti Saha with the blue one, then I am there, then here is the MD of the REI. Here is the New Science Creator Institute. Last year we received on New Science Creator Institute, which has taken a challenge to go for, it's a production of our hydroelectric cell pilot plant. Dr. Jyoti Saha and myself in the center, and there is a Central Electricity Authority, the turbine person, chairman of that. Then the other side is the president of the ISGF. So this was this award, and this backdrop, they had asked us that a big backdrop you provide us. So it is on the electronic screen in the Lalit Hotel. So that was done. So it's the 2-1, you can see the US patent book chapters in elsewhere, which are the encyclopedia, extended encyclopedia on energy. We were invited for this. So we published in 2018 on hydroelectric cell, then again 2024. Invitation in a huge encyclopedia on the different energy system, so you can see from the elsewhere. Same is similarly I had received in 2015 on handbook on materials from the elsewhere. So not only this, looking at the other side and then getting into that level where the people really feel that it's something very new and it has to be taken up in a different way. So you can see the US patent, Indian patent, Again another Indian patent. We have filed more also. So there is a lot of different work which we have to do. There is no way out. So a boon for masses, green energy source, because it's now the green energy source. Societal impact for rural India, because it is a very good in terms of you don't need to worry, because solar cell is expensive. That's the one part. The other part is it works only in the light, particularly sunlight. But here you need not to give any light, only the water, so you can use anytime, anywhere. Anywhere, if you have the water, you can really run with this hydroelectric cell. The foundations of hydrocell in the green energy domain, which I have already spoken, right? But still, I'll show you that how the migration of our dissociated water split in H plus OH ion goes on this, and I don't know, it's not working with the internet. इसमें इंटरनेट नहीं कनेक्टेड है, चल नहीं रहा. Anyway, otherwise it was how the water molecules are appearing in our any oxide material, and then you can see on the one side silver. We have already animated that how that water split is happening, and that is this. The reaction you can see, potentials you can see, that have been already published in our first paper on the hydroelectric cell. So now when we come to the next stage, that hydrogen, zinc hydroxide, which I did not speak, because the zinc hydroxide which is being formed in case of whether hydrogen generation or the electricity, in both the case, and the zinc hydroxide is in nanoparticle size, nano size, and it has got a high commercial value. So forgetting about anything, whether we get out of it electricity or anything, so there is another way of generating the zinc hydroxide nanoparticles, which has got this. So you can see that working of hydroelectric cell, I have already spoken that whatever is written over here, it's a completely indigenous. It has a miracle basically. But when we talk about here, so it is a 21st century's biggest invention. It's a well known. It is already available in our title of the papers, which are published in the international journals. Then alternative solar cell and fuel cell, this is also well accepted, because we have already crossed now. That time we were trying to approach, but now we have crossed it. So that way, hydroelectric cell, you can see that how it can be. Another most important part of the hydroelectric cell is that every part, even tomorrow you dispose it, because like a solar cell, silicon is the biggest problem. Solar cell disposal is the biggest problem as a big electronic waste. But in this case, there is no disposal issue, because anything you put into the soil, you put in water, air, everything is biocompatible, whatever we are using. And that is why we have opted oxides and only ferrites. This is the paper which is originally what it shows, that how it is working and what is the role of nanopore, because one of the nanopore has been put as a cylindrical form in the bluish side on this side. It will not work on it. So you can see that these are the reactions, what are the potentials, and International Journal of Energy Research, which was our first paper, where we gave them that what is the working principle behind it, role of nanopores to split the water molecule more and more. Technology readiness level, which is most of the time is asked, so TRL 6, we are already at a TRL 6. That's the very advanced stage, which even though working in the lab or institute where we do not work on it. Now the key highlights have been shown. You can see very clearly that there is a circular 2-inch square in the first photo where you can see the 3-watt LED bulb is being run. This we tested during the COVID time. We were running in the lab. For 300 hours we tested with our cells. We use 3 to 4 cells because we have to get at least 3 volt, 2.7 volt for any of the LED to start. So you can see here, that's the brown color circular one is our hydroelectric cell. On the other side, in the second picture, you will see the white. That's a SNO2 based. That also what we have published. So on these small cells are there, even 1-inch square, and you can see that how the bulb is being done, and then again the lamp, and then the last you can see inside of the earthen diya, we have put the 3 hydroelectric cell there as a small pellets in the different form, and 1 LED. When we put a water, then the diya is functioning as a diya. So it's a green diya which we have again coined in 2018. So we have been working throughout from the beginning how it can be used. So it has a lot of applications, but that all we have done in our lab, how this to be done. So small to large scale, what are the applications? How these are to be stacked inside a box like a battery. So hydroelectric cell 3 by 3 inch because we are doing it. So we connect them this way, so you can see. You can see some of the real picture also of the diya over there. But now the challenge comes where we are working for it, that how to produce in a large quantity. It is not a lab level, but a large quantity. So this kind of a pilot plant we are working on. In a large scale means we can process at one time 200 kg of our material, so that we can produce at least 1,000 of the cells, 500 to 1,000 cells. Then this is we have already prepared a roadmap for it, and then the furnace, then the rotary furnaces, how it is to be done, so that we are working. For the hydrogen again, that if we have to go for the hydrogen production out of because you need the cells. The problem is you need a large number of cells to show it, because any of the electrolyzer, even which is a 1 megawatt, the size of the electrode is in meters, 10 meter by 5 meter, and that is because they are using the metal as a electrode. But in our case, we cannot do that because it's a ferrite material, oxide materials, we cannot get that big. But definitely we have another scheme that how to stack them together and to find out this. So comparison hard cell, solid state, if you look at, which I have already spoken to you, that the efficiency is in our case is more than 70%, electrolyzer is 60 to 70 for producing the green hydrogen. And that we have done for magnesium ferrite and as well as for the tin oxide. So you can see the comparison everywhere will find it's a much better than any other one. So this is again India's big leap in green hydrogen production, because this can put a big leap. How we will be using it, how we will be doing it, but the problem is that some hard facts are already there. Electrolyzers don't work day and night, but the average working hours of an electrolyzer is only 5,000 hours a year and approximate 8,760 hours. It is worthy to note that with low operating hours, investment cost will dominate, and already the electrolyzers are in the hundreds of crore price, which we are importing. All the big companies, I don't want to name, they are doing it. So coming to global scenario, then the only answer comes to according to an estimate, if you read the top line, and estimate eventual global demand for hydrogen center around a figure about 500 million tons. And I will conclude within 5 minutes. I'm at the end. So that way, if you look at the global scenario, the situation can be overcome by only incorporating the existing green hydrogen technologies, and that what is already being accepted, it has been accepted at a global level. It is not that, because if we are able to publish the papers in that one, high-end journal, this is a small prototype. You can see that in the lab. This could also run, but I have tried earlier also, it cannot be run. Otherwise, you can see that how simple is it to produce the hydrogen in this. And the paper which we have published on hydrogen on this also. Because any claim which we are making is only based on our validated and recognized work. It's not that at international level, not for the Indian. So then it has a lot of benefits. Climate change, superior battery waste management, all these are the plus point of our hydroelectric cell. So cost effective and safe, dual benefits, and on this we have worked, because as a one example we have given for the SNO2, but the most of the work we are following with the first magnesium ferrite, because that we have really worked for last about 18 years, that how good that material can be fabricated. So that's a pure tin oxide cell prepared for hydrogen generation. You can see that what I was speaking to you, what are the steps into it, that what are the cells, how the tin oxides can be put, and you can see that hydrogen rate for the small pellet 2 into 2 centimeters square. But if I take it from 3 inches square, so then 100 ml per hour for single pellet. But because anything is not done for the only by 3 inches square, as I have told you, it is done in square meters. So that makes a comparison how we do it. We do the characterization. It is not that simply the work which we are doing, then most of the time we talk about the company or the technologies. So we just say, okay, this is this, that. But we keep on working everything on it, whether this microstructure is to be seen, whether it's a cyclic voltammetry by that, what voltage it is giving, how is happening, how the binding energy is changing of our SN2 plus and SN4 plus, because it's not that the only SNO2 is being used as a hydrogen, but we are working on them. You can see our XPS results also, that what is happening to our binding energies, what is being reduced, whether by SN2 plus or SN4 plus, because SNO2 when we are using, so we can control both of them, and which is taking our lead. So that way it is not the simply doing and showing the hydrogen production or any device to work, but we are doing a lot of different kind of. So we have gone for the SNO2 Fe2O3 composite base cell, and here you can get around 0.4 milliliter per hour by the again single cell. So it's a huge amount. With the simple setup you can see already. Composite characterization, we have to work on them. We have worked, and we have to send this work for our publication. So the industrial R&D pilot plant for hydroelectric cell, which I was talking to you. The most important part is this one, that's the last of my deliberation. That if you read that HTTP link over there, it's a market research on hydroelectric cell, 180 page from the US, one of the marketing research one. So they are picking themselves, and in the last 4 years, these people different companies have put in, looking at the best one, the other one has also published. They have created a report of 250 pages where they have predicted that it can go up to by 2030 to 2031, means after 5-6 years, they are considering it to be $2.1 billion business. So they are doing it, not we. So no Indian company, but the US companies are doing it this way. They are predicting. But this predictions is based on the whatever the work has been done. But what is to be done, that finally comes out to be that it should be in the production. If it is not in the production, then it will remain as a whatever it is happening. Thank you. Any other question, because you have asked in between? Yes.
I wanted to ask whether wastewater could be used in this process, or what the quality of water should be for the electricity generation.
It's a good question. It can, it is sensitive for the water. So you use the wastewater, you use the seawater. We have used the seawater also, right? Because we had tried in all the way, because these are the ways which we have been doing. What is happening? Only problem with this one, if let's say I use the wastewater in which there are the particles, and I have told you it is a nanoporous. So if these, we have to use some filter, at least some particulate matter should not be there which will damage this, right? Because once they get in on the surface of the hydrogen cell, so those nanopores are exposed, so they will clog the nanopores, then its efficiency will decrease. So we have to use a filter, like for if we have to live in a better way, so we are using the RO water, because the water quality is very bad, or the other one. But at the moment we are not doing anything except all the results, all the work is being done on DI water, 16 mega ohm resistance. So that nothing should be shown as that something bad is being done, Yes, please, sorry.
Thank you. It was an excellent lecture. I have two questions. One is that, do we have a commercial product in the market regarding this?
No, this is what we have done in the institute, right? We want to bring it this year by end.
And so
Small.
what could be the scope of further research in this area?
Research area is abundant. It is a very big thing, and that was our initial idea, me and Dr. Jyotisha, because in fact I was planning everything. So the different people are associated with me. Very senior people are also associated with me. At an initial stage, we have worked on the different oxide material, different one. I did not want that hydroelectric cells should be limited by a silicon solar cell only, because solar cell, you know very well, there were the 5-6 different compounds which were being used. Even the organic solar cell had come, but that was a different working principle. So all those were winded up, and the final outcome as a application part of it has been the only silicon solar cell, for which I was working. I did my PhD on that, right, on solar cell, way back 1985. So the point is, we should not be limited to the material. So many materials I was working in. From our lab, we have produced 29 compounds, new compounds, on which the hair cell is framed, but of course not this much level, slightly lower.
Other than oxides as well?
Yes. Then the other people have added, they are also working, they have also added. So it's the only benefit is that we can work on the broader platform. So anybody can work. So if someone is to do not for the product, but for the research work, because that will give us some idea. So that is why they can choose the titanium dioxide, they can use the SNO2, they can use the magnesium oxide. We have published on that already. But those are the first paper. But after that, there is still a lot of opportunity which is being done. So a big scope for the research in this area.
And what would be the key parameters for enhancement of?
Key parameters is most of the time material synthesis. How much oxygen efficiency we are able to create in our material during the processing, and what is the size of our nanopores is being generated in the material.
Thank you, sir.
Thank you, sir. Now, it is my privilege to express my heartfelt gratitude to you, sir, to Professor Kotnala, sir, for your insightful and inspiring address. Your valuable thoughts, depth of knowledge, innovative perspective have truly enriched this session and provided all of us with meaningful insights. We sincerely appreciate the time and effort you have taken to be here, sir, and to share your expertise with us. Your guidance and presence have added immense value to this conference and have made this session even more meaningful and impactful. Once again, thank you, sir, for your gracious presence and for your inspiring words for making this session so engaging and enlightening. Now, I request Dr. Neeru Sharma ma'am, co-convener of this international conference, for presenting Certificate of Appreciation to Professor Kotnala sir for successfully delivering his keynote address. I request to please come forward Professor Kotnala sir and Dr. Neeru Sharma ma'am. Please everyone give a big round of applause. Now, I also request Professor Kotnala sir to kindly chair the upcoming session, and I'm sure your insights will greatly enrich this session. प्रेजेंट करेंगे ना इनवाइटेड टॉपिक माइक Hello.
Good afternoon to everybody in the auditorium. In this session, I invite Professor Kanuparna Sachdev from MNIT Jaipur, a learned speaker who has to speak in the energy. And I came to know that she is going to talk something different than what I was speaking. So let's have a good comparison, right? Her talk, I'll let you know that she has got already more than 100 research papers published, guided 15 PhD scholars, and her today's talk is on aqueous sodium ion batteries, synergistic effects of cation doping and electrolyte engineering. So please.
Thank you, sir. So, good afternoon, everyone. And we are running late, it's lunch time, but still I think you'll have to bear with me. I'm Kanupriya Sachdev, Department of Physics, MNIT Jaipur. I thank the organizers for giving me this opportunity to share some of the research work my students are doing. And I will be talking on the aqueous sodium ion batteries. So let's just start. This is quite clear. The rise of the demand for energy worldwide has led to people looking at renewable, giving more emphasis to renewable energy sources, and the intermittent nature of the renewable energy sources makes it essential that we have battery storage techniques. So there are different battery storage techniques. Out of them I will be talking about the energy storage techniques. Out of them I will be talking about the batteries, and specifically the sodium ion batteries. So lithium ion batteries till now, actually the research on both type of batteries, the lithium ion and the storage, the sodium ion, it started at the same time. But because the excellent results delivered by the lithium ion battery, the research on sodium ion took a backstage. And for the last 20 years, it has been the most favored battery for portable electronics, electric vehicles, and other applications. But recently, I would say the last 10 years, the research on sodium has picked up again. There are many reasons. And I would say that the sodium ion battery technology is not here to replace the lithium ion battery, but to complement it. So again, the reasons are different. The reasons are because it doesn't give you the same energy density as by the lithium ion. So definitely it cannot replace it in all applications, and therefore the places where this battery technology will be relevant, we will have to emphasize on that. There are several drawbacks of the lithium ion technology, and because of these drawbacks, the material, the material lithium is a material which is of course not distributed globally properly, and the extraction is not that easy. It is quite complex. Compared to that, the sodium resource is available, it's cheap, abundant, and its extraction is also quite green. So in terms of the green energy and in terms of the economic relevance, there is a more emphasis on the sodium ion technology. Another thing which is favorable for the case of this technology is that this technology can, because it has the same technology, so wherever there are systems built to produce a lithium ion battery, the same technology can be used for the sodium ion battery also. So these are the factors. These sodium ion battery is becoming more and more important, and people are looking at having different materials giving you higher energy density. So what is a sodium ion battery? It is just a rechargeable battery. The cathode, which is the positive electrode, is normally made from a sodium based materials, and the anode is typically a hard carbon, which is unlike graphite in lithium ion. So the electrolyte, it could be a liquid electrolyte, a gel electrolyte, or a solid electrolyte, and the current collectors, that is again advantage in this technology is that instead of copper, you can use aluminum on both the sides. The working of the battery is the rocking chair mechanism, which is similar to the lithium ion battery, and it finds various applications. So it has already gone on the industry level production, and China has taken a lead, and there are many companies. India has also started in this, and there are many companies producing sodium ion batteries on commercial level, and they are being used in various applications. As I said, the cathode material has to be which contains sodium. There are mainly three categories of materials used for cathode for sodium ion batteries. One is the layered transition metal oxides, on which I will be working on, and then polyanionic compounds and Prussian blue analogs. Each of the categories have their own specific advantages and disadvantages. Now, why aqueous? Now, if we go to non-aqueous, then of course the results are better. But the aqueous ion battery has its own advantages. What are the advantages? The advantages are it gives you high ionic conductivity, it gives you superior safety profile, the low cost and availability of the aqueous electrolytes, and of course it's eco-friendly and sustainable. In case of non-aqueous electrolyte, the ionic conductivity is less, there is a high flammability risk. We can use the ionic liquids there or the organic. Of course, the materials are very expensive, especially the ionic liquids, and there's an environmental impact. The strategies which the researchers are using to improve the performance of the cathode is having a surface coating or doping in the cathode material, working on the design of the material structure, construction of an artificial interface layer which improves the electrochemical properties, and regulating the surface character of the electrodes by various methods. So these are the three materials which we talked about as for the cathode, and these are the different strategies for enhancing the characteristics of the cathode material. At the same time, people are also working at widening the electrochemical window and improving the cyclic stability, because as they are two important characteristics of a battery. Now, in this case, the strategy could include adopting a highly concentrated or a gel electrolyte, introducing additives in aqueous electrolytes, or passivating the oxygen evolution reaction or the hydrogen evolution reaction on the surface of the current collectors. Now I will talk about the layered transition metal oxides, which is one of the very important category of cathode materials used in sodium ion battery. These layered transition metal oxides, they have several advantages. The properties of they have a layered structure, they have an easy synthesis process, high theoretical capacity, and depending on what type of layered LTMO you are using, you will get a fast diffusion of sodium ions, the redox between Mn3 plus and Mn4 plus, giving you high electronic conductivity and easy to tune structure. So these are the various properties which make them favorable. Mostly these materials can be categorized into two types, O type and P type. What is the difference? The difference is that where the sodium ion is sitting, in the octahedral position or in the prismatic position. So in the O type, the sodium ion occupies the octahedral site. What are the advantages? It has a high sodium content, so it gives you a higher energy density. But the disadvantage is that it has a complex structure, and that results in hindrance in the movement of the sodium ion. Compared to that, for P type, the sodium ion occupy the prismatic site, belongs to a particular hexagonal space group. The sodium ratio is lesser in this case. It is between 0.44 to 0.7. If we go less than 0.44, we get a tunnel structure. So the layered structure starts from 0.44, and after 0.7, we get the O type. So it has a low sodium content, and there are phase transitions during the cycling and that means the charging and the discharging processes. But it provides an easy diffusion path for sodium ion. So in this particular study, what we see is that they have tried to improve upon this. This is a tunnel structure material, Na.44 MnO2, and the copper doping has been done to improve the properties. Why copper? The challenge which was addressed in this study was the narrow potential window and limited cycle life for the pristine materials. So this is a 3 electrode study. So if we look at this figure, the B figure, then it doesn't work on the screen. Okay. You can see cracks in the material, which is post-cycling. This is the post-cycling SEM of the material, and these are the cracks in the material which are occurring in the pristine material. But in the copper doped material, they are not there. So that increases the stability of the material. And these figures are related to the charge discharge and the rate performance of this cathode material. And if you look at the figure G, then the capacity retention, the cyclic stability for 2000 cycles, for 2000 cycles is much more in the copper doped sample. So, as I said, we could see in that picture the structural cracks appearing for a high number of cycles in the pristine sample. But the copper doping in the sample, it expands the diffusion channels, it mitigates the strain, and of course it suppresses the voltage decay during the cycle. So that gives you an enhanced electrochemical properties of the material, and the copper facilitates the easier diffusion of sodium ion, removing the barriers. In this study, there is a mixture of electrolytes. So that means this is a strategy of having a hybrid electrolyte. And this hybrid electrolyte, it prevents the in situ protection of the phase transition during cycling, and suppressed electrode dissolution for the aqueous sodium ion batteries. So if you look at the results, then it is quite clear that this AWE, this is the hybrid electrolyte, and the hybrid electrolyte has better stability, more capacity retention for long cycling. So what the hybrid electrolyte does is that it affects the solvation of the sodium ion, and this unique solvation structure, it expands the electrochemical stability window to 2.75, also alleviates the dissolution of the vanadium based electrolyte, of the vanadium based electrodes. So we have a high coulombic efficiency, and we have a better capacity retention for 1000 cycles at a high current rate, which was 5C. Now this is the study which we did and was published in ACS Applied Materials and Interfaces, and in this we used a dual strategy of doping as well as using a hybrid electrolyte. So the doping was done initially of copper and iron. And why we chose copper and iron? So because the copper doping enhances the covalency, and it mitigates the Jan-Taylor distortion of the manganese ions. So these are two important things. And iron incorporation, it stabilizes the lattice. So using these two elements, we have tried to improve using the doping strategy. And the second was adding ethanol to water, making a hybrid electrolyte, which facilitates hydrogen bonding with molecules and effectively modulates the electrolyte's solvation structure. These are the SEM. NMO is the pristine sample. NFCM is the sample with copper and iron doping. These are the elemental mappings confirming this. The X-phase was done to find out the elemental composition of these materials. And these are the cyclic voltammetry plots. The cyclic voltammetry plots, through them we found out the capacity, and these are the galvanostatic charge discharge profiles and the cycle life. So the NFCM sample, that means a sample with copper and iron doping along with the hybrid electrolyte. So we had 4 samples, one pristine sample with the aqueous, that means plain water. Then we had the doped sample with plain water, and then the pristine sample with the hybrid electrolyte, and the doped sample with the hybrid electrolyte. So out of these 4 samples, the sample which was doped and was having a hybrid electrolyte gave us the best results. These are the Nyquist plots to find out the series resistance and the contact resistance of the device, and to calculate the diffusion coefficient. The diffusion coefficient was improved for the sample which was doped in the hybrid electrolyte. So the copper doping suppresses the Jahn-Taylor distortion, improves the structural as well as air stability, because these samples are known to be air sensitive and moisture sensitive. And iron doping reduces the migration of the manganese ion during cycling. Ethanol enhances the solvation structure, strengthens the hydrogen bond, and controls the proton activity. So the doped material retains 91% capacity with 100 cycles, giving us a very good value of 135 milliampere hour per gram capacity in the hybrid electrolyte. Now this sample was further doped with lithium and titanium, and in this the purpose was to increase the cycle life. So the objective was to increase the cycle life, and doping with lithium and titanium, these are the various microscopy figures and the XPS to find out the elemental compositions. And we did some post-cycling study also in these samples to find out the variation, that how their structure and the elemental composition, whether they are getting degraded during the cycling. So the rate performance of this material was quite good. These are the charge discharge cycles, the Coulombic efficiency retention, and the capacity retention for 1500 cycles at a 10C current rate, which is quite high. These are the EIS plots to find out the series resistance, the charge transfer resistance, and the diffusion coefficient. In this case, we had a very good result, that we could see that there is a very small increase of the series resistance, almost negligible increase of series resistance for the lithium titanium doped sample for 1500 cycles, and a very small increase for charge transfer resistance. You can see it is only 2.1 to 16.6, but for the without lithium titanium doping, it increases from 5.5 to 272.1. We checked the structure of the sample. As I said, we did some post-cycling studies also. So you can see that these are the cycle numbers. So after 200 cycle, 400 cycle, 600 cycle, and 800 and 1000, we took the XRD of these samples, and we could find that there was no appreciable change in the structure of the cathode material. The peak positions were the same, and the microscopy pictures show that for the lithium titanium doped sample, there was no visible degradation, but for the sample which was not doped, there was an agglomeration of particles, and they were, getting bigger in size after cycling. So we could conclude that the co-doping of lithium and titanium at the manganese site, it improved many things in the sample, suppressed the JT distortion, mitigated oxygen evaluation, capacity retention was 79% over 1500 cycles at 10C in 1M Na2SO4, and the post-cycling XRD, Raman, and XPS, of course they were XC2 all, we could see that the crystallography was preserved, and the ratio of, from the XPS we could find that the ratio of manganese 3 plus to manganese 4 plus was stabilized with minimum phase degradation even after prolonged cycles in the doped sample. So with this I conclude my talk. Thank you so much.
You have heard Professor Kanupriti Priya, that she has nicely described that how sodium ion battery would be used as a supplement to. I have one question. As a you have said so that it is to be a supplement.
I said it is.
Grouping of the lithium.
Lithium basically is an electroactive material, so that's how it contributes to the capacity.
To the capacity. Anyway, because he has taken care of the time, so one or two questions can be asked.
You said that with copper you are able to change the yarn-Taylor distortion. So I was
Not
interested.
change, suppress it.
Suppress, yeah. So how it works? If you put copper, how the splitting changes? Because that's essentially what it is, right? The yarn-Taylor distortion, you have an isotropy within the plane and with respect to out-of-plane forms, right? So I was just thinking if I put copper is replacing manganese, is it?
Yes.
So the balance of manganese is getting changed?
Yes. So it is affecting the structure basically.
So most probably the manganese balance is getting changed when you put low copper there, and that will result into change.
Into lesser distortion.
Any other question? I think you have nicely explained your presentation. So not many questions are there. So thank you very much. Please, UB for taking the presentation from the organizers.
Thank you.
I think next speaker is again from NIT Jaipur, Dr. Vikas Sharma. He has got a 15 years of research experience in next generation photovoltaics and transparent electrodes, and has worked with reputed institutions including the Hebrew University of Jerusalem, IIT Bombay and IIT Delhi. He has published 35 research papers with over 1500 citations and is recipient of the UGC IUAC Beam Time Award. His title of the award is Beyond the Silicon, Flexible, Semi-Transparent and Colorful Solar Cell. So the Dr. Vikas Sharma, we welcome you to please deliver your lecture. And you can maintain the time.
Sure.
Already CSF.
Yeah, I am between the lunch and your hunger. So thank you, Professor, for nice introduction. I will not take too much time, and I still believe solar cell will work. The previous lecture says solar cell time is gone, but I still believe solar cell will work. So it's fine. I am recently joined as an assistant professor in Malvi National Institute of Technology. It's just 1 month, so I'm new to this academics. Before that I was just in a scholar. I hope this side also visible the screen. If not, you can shift here. Before I go for my lecture, I have two announcements. So first announcement, we are launching, I joined in the Material Research Center in NIT Jaipur. We are launching a course. That course is MTech, the MTech program in semiconductor devices, because you know now the industry is moving towards the semiconductors. So if you or any of your friends or any of the scholars want to join that ambition mission, we are welcome you. The course is based on the semiconductor technology and device engineering. We are ensuring you will get a lot of good things and definitely a good job for sure. And we have the PhD program also. If you are looking for a research, you are also welcome to join. There is like a lot of faculties are there. We have the new center with all the facility from fabrication to the characterization. So this is the first announcement. You can contact, you can scan, and you can mail me, or you can directly contact to the department if you have any queries. I joined here, so this is my only group. Everybody shows a group. Ma'am, she's my supervisor also. So we have the big group, but now the group is only me. If you want to join me as a postdoc candidate, as a PhD candidate, or as a master student, you are welcome. For the internship also, if you are a graduate student, we have the internship program. You can see the MNIT website. There we pay also some amount, a minimum amount. So you can come as an intern also. This is, we work on mainly on the energy, optoelectronics and semiconductor devices. And I will show you some of my work, but we are expanding. So if you have the good idea, we can open to discuss. So these are my two announcements. Now I move back to my presentation. Israel. Everybody think Israel, we have the only bombs and the shelters, but no, we have the other things also. I was there for 3 years, and believe me, it's a safe country. You can go and enjoy. We have a lot of nice beaches, including Dead Sea. And we have the good infrastructure of trains, and it's a holy land where I live. I lived in Jerusalem, so it's one of the holy land for the few of the religions. So, but overall, it's a nice country. These are my groups. Slow-mo, this one is Nobel nominated, work on the 3D. I work with the device with the LEOs. We work on the halide perovskite mainly for the printing of the halide perovskites. We'll discuss. This is my campus. We have the 5 campus in Hebrew University. I work on the Givatram. This is for science and engineering. Now I move back to my home institute, which is NIT Jaipur as an AP. I started my PhD journey with the transparent electrode, which is like essential for any of the devices, either it's a solar cell, phone, mobile, TV, anything. We want to create alternative of the ITO, which is like scary material. So we do the DMD structure, dielectric, metal dielectric. We check it for the harsh environment application in the ion irradiation, and we check it. Then I move to the another material which is called halide perovskite. This is a new semiconductor right now. Everybody is talking about it. The thing is that it's showing the property. Why? It can absorb the light from a very less light. Absorption coefficient is 1 time order higher than the silicon. So we can use the solar cell of the halide perovskite inside also without. It's stable. We can tune the band gap because we have to tune the structure. We tune the halide and we can tune the band gap and low temperature coefficient. So we can make it at the low temperature. So it's energy efficient. Lot of applications are there around the world. People are working. My area of work is mainly in the transparent devices. So I will talk mainly 2 things here, BIPV and the tandem cell. Tandem cell required NIR transparent solar cell, while the BIPV required visible transparent solar cells. So let's go for tandem. This work I did in IIT Bombay with Professor Dinesh Kabra. And what we did, we had the silicon solar cell. We put another solar cell on this. So we make a tandem solar cell. So what is the benefit of this? We can split the spectrum. The bottom cell will use the spectra from 800 to 1200 nanometer, while the upper cell will use the bottom one 400 to 800. So we can increase the spectrum of absorption and we increase the efficiency. We can see we change the one particular problem is that we have to deposit the top transparent electrode, which we can't do with the normal sputtering. So we modify the sputtering setup for the normal. With the 2-inch target, we are getting 3-inch yield and without damage. And we also use the copper because the scarcity of the silver and another material for the bush bar is also a big concern in the solar cell industry. So we go for the copper also. We fabricate the complete NIR transparent devices and also, Also the tandem device. We get a tandem device from the PERC and BRC cell, which is NCPRE provided. And we reached, it's in the 2023, we reached up to 26%. The silicon limit is generally 23%. We reach up to the 26%. My lab right now is moving up to 31%, which is the lab scale. And the word efficiency already reached to 35%. So the barrier of the science is already broken. We can go beyond the barriers. That's why we can say like silicon solar cell is still remaining. We are not changing. We are just putting something else on it, and we are increasing the efficiency. And 1% efficiency change in the energy will change a lot of, because we are working in the gigawatts energy with the silicons. Now we move to the visible solar cell. This is for the large area. But what about the buildings? You see the lot of buildings, colorful buildings in our Delhi or new cities like Mumbai or New York or anywhere. Can we use them as a energy efficient building? We can make a solar cell which can also absorb and also have the transparency. So we can, instead of your curtain, this curtain, if I put a solar cell here, so we can see through it, and they also use as a solar cell. So that is the work. The first challenge, I will not go technicality in this. The first challenge is that we have to make it on the flexible, because we want to make it bendable. Nobody want a glass very hard to put and change the glass. We just want a sticker that can be stick. So we want to make it low temperature process. So what is the technology we use here? We didn't use the temperature, we use the plasma as a annealing temperature. So we use the plasma as an annealing temperature and make it low temperature, medium temperature and high temperature. And with all the optimization, because time is limited, I will not go for this. If you want, you can check my paper and discuss with me. We check that with the 10 minutes of 100-degree annealing and 10 minutes of immediate plasma treatment, we use that plasma as a source of annealing. We found there is no change in the absorption, no change in the PL, which is like emission spectra, and even if a better lifetime of the perovskite with this kind of a electron transport layer. We make a complete cell. The cell with the medium like 100 degree, this is the 60 degree, this is the 180 degree. 100 degree is appreciable because my substrate can handle 150 degree. So this is appreciable, and you can see if I go for the voltage, there is a minimum variation. These are the 16 cell variation. This is not only the one cell. So the variation is also less. So we can use the plasma. You can see the real cell. This is in my hand and this is my lab. You can see through my lab's glove box behind it, and we make, and the transparency is around 25% and efficiency is 10%. But the most of the people change the transparency by changing the band gap. But the problem with the halide perovskite, if you change anything, they will not stable. They will not stable in the journal also. So what we want to do, we want to change the transparency without changing any composition of the material. So what we put 3D structure in that. They are the hollow holes, like they are the pillars. We print through the 3D printing. In between the hollow spheres, like these are the holes. Through the light will go, and these are the perovskite. Now it will absorb the light and you will get energy. So we make this kind of a cell. We check they are stable because we use a lot of solvents, organic solvents. They should be stable. They are the green. So we don't use any of the toxic solvent, no DMF, nothing. They are printed without solvent. We just use a monomer, print it, UV cure, and they will get it. We check it with the, again, can we able to change the transparency, and you can see once I increase the number of the pillar, I can reach up to 35% transparency from 25 to 35%. So they are working, but they are not changing the any property of the my perovskite. They are not reacting with the perovskite. So it is also stable. So we make the complete device, check the cells are working. We are very happy, but they are black. Oh no, before that they are also stable. We check the different bending capacity also, because they are flexible. If I put on the some of the window, they may be curvy. So we check the bending, how much we can bend. You can see here in the mm range. So we bend up to 5 mm also, and they are working. And with the pillars, once I include the pillar, it will increase the mechanical flexibility also, or I can say mechanical stability also. Why? These pillars are putting a barrier to the any of the defects. Mainly generally the cracks occurs, they will stop by these pillars in between the cells. and we have the open environment. People say perovskite is not stable. This is not true. They are the humors. Perovskite is stable. People are working on that. So you can see we are having the open devices. They are encapsulated devices. We check them up to the 1200 hours. They are working. They degrade up to the 80% of the initial efficiency. But if the packaging is done, we have the commercial also. So right now the people are also having the commercial. Last month people are launched 12-inch wafer with the 30% efficiency of tandem solar cell. So they are efficient. Then the challenge is nobody want to put a black silicon solar cell on their window. They put a crores of rupees in India in the house. Nobody want a black kind or brown kind of a solar cell. We want something very attractive, light color. So how can we change? So we want to put a change, but if I put something extra layer for the color, it will hinder my transparency. Second thing, it will increase the cost, and we have to think commercially. So I use just a 12th class, you also using this concept, just change the thickness of internal reflection path length. We change this and use the DMD electrode. I change the top oxide thickness, here is the MOX, and the path length is changed, and we are getting a reflection from the different light. So I use 4 kind of a thickness, 15 to 45 nanometer, and we can change the 4 thickness. You can see, if you see the CIA diagram, we are getting a 4 different color. So I can choose the thickness, I can tune the color, and my efficiency is not changing too much. They are little bit affecting, but I am getting a nice VOC, and current is little bit changing. So, these are the colorful cells. These are real devices. If you can see, there are the pillars, they making it stable, but you can see the colors. From 15 to 45 nanometers, we are changing a broad spectrum of the color. So you can put them, they are flexible, they are colorful, they are transparent. These are the entire process which is we use. I sum up here, and they are used for the building integrated photovoltaics. We already, not me, my group already opened a commercial company for that, and we are launching this soon as a commercial. These are my future scope. I return back to here. I think these cells are more stable in the space. We don't worry about the moisture, we don't worry about the oxygen, but there are other different challenges. So I am in my future direction, we can print because they are very lightweight. You can print for the space missions, and there also from here also. So few groups are already working on it, including me. We are working on the different part of this solar cell, because somebody is working on the electrode, somebody on the material, somebody on the complete devices. These are my idea. We can go for transparent one, and we have to check with all these parameters if we want to go. If somebody of you are interested, let me know. Before I work on when I was in IIT Delhi with Professor B.R. Mehta, we work on the gas sensing, and this is a special slide. When we work on, Neeru and me are on the same group, and we working on this. Why I am showing this slide? When we are discussing, we found that no, results are not quite good for go for a journal. So we put on a conference paper which published. But that doesn't mean, if you work honestly, if you see the citation, a conference paper is cited more than any other paper, and this paper is cited by at least more than 10 times in the Nature. So this is the strength of the science if you work honestly. So I always appreciate Neeru for this kind of a work. Like, she put all the honesty in that, and that's why we are getting this kind of a citations in a single paper. So thank you, Neeru. And these are my conclusion. I am running out of short of time. My chair is looking at me. So thank you all of you. These are my research collaboration all around the world and India. This is my IIT Bombay group. This is IIT Delhi group. We lost our Professor B.R. Mehta few months back. So I can say I dedicated this talk to Professor B.R. Mehta, where I learned a lot in TFL. Professor Pankaj Srivastava was also there, and we learned a lot from there. And this is my group. I think I look same. This is my 10 years ago picture, so it's good for me. Thank you, everyone. Any doubt before the lunch? I think no doubt. We should move for the lunch.
There must be some questions, I think.
They are hungry.
Anyone can ask any question, but I have one question before anybody asks you the question. You have used copper in place of the silver in solar cell.
Bush bar.
Right?
Bush bar.
Bush bar.
Yeah, bush bar. We coated the bush bar with the copper. We check with the copper, aluminium and silver, both. All three.
All three.
Yeah. And copper is also working fine.
Copper is also working. But how you are able to make a ohmic contact with your silicon?
No, it's for the perovskite. It's on the top cell. That's why.
It's on the perovskite top.
On the top. So, because in the tandem we have the perovskite on the top. So we are not worried about the silicon contact. We have the interlayer. It's a 2-terminal, then interlayer. If a 4-terminal, we have there silver contact. But for the perovskite, copper is also working fine.
No, but this still it is taking it's a contact point from where you are collecting your charge.
Yeah, because we have the ITO on the top, IZO. So we already collecting a charge on the ITO. To remove the series resistance in the ITO, we put the bush bar. That is the copper.
So ITO you have put already. So
Yes.
Fine. Any other question, please?
There is a back question, or you are just waving someone else? Okay. No question.
No.
No question.
Anyway, I think nobody is asking more questions. So we really thank Dr. Vikas Sharma for the very important topic, particularly flexible solar cell.
Thank you.
The multi-layer. So I believe that this work will flourish even in MNIT.
I hope.
Thank you.
Thank you.
I request our esteemed chairperson, Professor R.K. Kotnala sir, to kindly felicitate Dr. Vikas Sharma sir as a token of our appreciation by presenting him a card and a memento. Please give a big round of applause.
Now we'll move quickly to the next speaker. It's a oral presentation. Miss Deepika Sharma from Central University of Haryana. I'm sure you will complete it within 10 minutes. Her title of presentation is Structural Ferroelectric and Luminescence Behavior of Sodium Modified Barium Calcium Titanium Zincate. Sorry.
Zirconia.
Zirconia ceramics. So please, I think you can begin with that.
Good afternoon, one and all present here. Myself, Deepika Sharma from Department of Physics and Astrophysics, Central University of Haryana. I am in second year of my PhD, and my topic is Structural Ferroelectric and Luminescence Behavior of PR Modified Barium Titanate Based Ceramics. This work mainly focused on developing multifunctional materials for next generation applications. So let me begin with the motivation. The motivation arises from the already existing piezoelectric materials which are toxic and environmentally restricted. So we need to develop materials which are environment friendly. Although we have materials which are lead free, but still they suffer from low performance and high processing conditions, which makes it restricted for commercial use. So we need also at the same time the modern devices demand next generation multifunctional devices. So we need to develop materials that are lead free and multifunctional in properties like electrical or optical. So I choose for my work barium titanate as base material. Why barium titanate as base material? Because it is structurally stable, it's lead-free nature and compositional versatility. Also, its piezoelectric response is high, which makes it highly tunable for doping, and a large dielectric constant, which makes it suitable for energy storage applications. This barium titanate material is sensitive to defects, which offers us opportunity to alter its properties via doping. So its performance strongly depend on defects and processing conditions. What idea we got? My strategy is based on stoichiometry tuning to optimize electrical properties, reduce defects by controlling oxygen vacancies, and also these materials show optical properties by rare earth doping. So I choose praseodymium as a rare earth for doping, and this shows luminescence and piezoelectric both properties, which makes it suitable for multifunctional devices. Um, Also, this work focused on optimize the sintering temperature for enhanced performance. So, what I have done, I briefly discuss about the structure of the barium titanate. This structure belongs to the perovskite family, which have the chemical formula AbX3, where X belongs to the halogen or oxygen. A is the monovalent or divalent cation, which is large cation. B is the tetravalent or pentavalent small cation, or uh, oxygen is the present at the face center of this structure. This barium titanate is highly flexible, so it gives us opportunity to alter its property by applying electric field, etc. Like in figure A, you can see the base structure of the barium titanate, and when I applied the electric field, this shows extension, which shows the polarization in this material, resulting the dielectric and ferroelectric behavior of the material. So this Boltzmann's tolerance factor T, which is used to predict the stability of the perovskite structure. Here represents the formula, which shows the degree of distortion from the cubic phase of the material. This slide shows the degree of degree of distortion from the cubic phase. Like on the temperature above 120 degrees Celsius, this material shows cubic phase, which means no extension, means no polarization. But when temperature in between 5 degrees Celsius to 120 degrees Celsius, the structure shows extension along height and polarization along 001 direction, which means it exists in tetragonal phase. Next, when temperature is between minus 90 degrees Celsius to 5 degrees Celsius, the structure shows extension along face diagonal and polarization along 110 direction, which makes its orthorhombic phase. And the next one is less than minus 90 degrees Celsius, extension along body diagonal, polarization along 11 direction, and the structure exists in rhombohedral phase. Now, this material has a wide-ranging application. Let me show you. The application, the material exhibit piezo-catalysis application, ferroelectric, piezoelectric materials, but due to rare earth incorporation, which I have used for my work, PR incorporation, praseodymium incorporation, makes it suitable for optical memory devices, for optoelectrical devices, and energy storage in bioimaging medical applications. Why? Because it shows both dielectric and luminescent behavior. So what methodology I have used to synthesize my samples? The solid state reaction method. This is the synthesis route which I have followed, from selecting the precursors, then grinding and ball milling in mortar and pestle, then calcinating the powder, after then mixing of binder for densifying the powder to make pellets, using the pelletizing machine for making pellets, and then sintering the pellets on different temperatures. And finally I got the pellets for further characterizations. एक्सक्यूज मी, ये स्लाइड्स में मिसिंग है डेटा, मैंने आपको जो भेजा था उसमें मिसिंग है। नहीं मैम, but the data is missing.
We will go to next
Can
slide.
I share my pen drive to you? Yes. मेरी pen drive देना please. Okay, without wasting your time, this is the XRD pattern of my samples, which shows the pure perovskite phase and pure perovskite phase structure, and this is the structure of the material synthesized from Vista software. I have shown ritual refinement patterns of my material in this slide, but I don't know how it disappears. But I think I should give it my pen drive. It's okay, ma'am. Okay. To further validate the validate the XRD pattern, I have performed the ritual refinement, and the ritual refinement shows that my pristine material exhibit in rhombohedral and tetragonal phase, which shows the material lies near the morphotrophic phase boundary, and the next three samples which are made at 1350 degrees Celsius, 1400 degrees Celsius and 1450 degrees Celsius, they exhibit the tetragonal phase only, which makes it good having dielectric properties. And the table shows the lattice parameters, volume and C by A ratio with the fitting factors like R factors and the chi-square value of the sample. Ma'am, all the data is missing. Yeah.
Next presentation is Piyush Siroha. Please provide your presentation.
Sorry everybody for the inconvenience. Okay, let me start again. Uh, it shows the pure perovskite phase and no secondary phase is observed. Also, I have observed the variation in volume with the sintering temperature and the C by A ratio, which is the tetragonal ratio of the structure. To further validate the structure, I performed the ritual refinement for the pristine and the all samples sintered at 1350, 1400 and 1450 degree temperature. The first one shows the orthorhombic and tetragonal phase, and the other three shows the tetragonal phase of the structure. This table shows the lattice parameters, volume and tetragonal ratio with fitting factors, chi-square value of the my sample. I have also performed the temperature dependence dielectric study of this my material, and it clearly shows the phase transition peak at near Curie temperature and maximum dielectric constant. And you can observe in the table the maximum dielectric constant is observed for 1400 degrees Celsius sintered sample. Why? Because PR incorporation makes it dielectric stability more accurate. I have also performed the dielectric dependence of temperature dependence dielectric study, in which I observed the tangent loss, dielectric loss of sample. It is also showing the dielectric stability for the 1400 degrees Celsius sintered sample, which is good for us. This shows the PE hysteresis loop. The PE hysteresis loop confirms the ferroelectric behavior, good ferroelectric behavior of the sample. It shows well saturated loops, high remanent polarization and moderate corrosive field value for all the samples, which makes it suitable for ferroelectric devices. And I have shown that 1400 degrees Celsius sintered sample shows the highest remanent polarization and the saturation value. This is one of the key results of my work, which is the photoluminescence behavior of the sample. This shows that when excitation wavelength for 48 nanometer is excited on the sample, then it shows the luminescence behavior and the peak for the 1 for the blue line and 2 for the green line and 3 red emission peaks, which makes it suitable for optical devices. And it shows down conversion when we excite material with lower wavelength and getting the light at higher wavelength, it shows down conversion. So this material is good for down conversion applications. And this table shows that 1400 degrees Celsius temperature sintered sample shows very good properties as compared to the other three. And in this slide, I have concluded the dielectric and ferroelectric results of my work. So I would like to conclude myself with the statement that I have successfully synthesized the material which has good dielectric, ferroelectric and luminescence properties, which makes it suitable for energy storage applications and for bioimaging and optical memory devices. So these are the references I have gone through during my research work. Thank you all for your attention.
Thank you, Deepika. If anybody wants to have a question to her.
Yes, sir.
Temperature just only 50-degree variation.
Yes, sir.
How do you control the 50 degrees? Because at the high temperature, 50 degrees, like we don't have the.
It's a minor difference, but still I have to perform this.
Change is too much. 1400 to
1450.
Change is too much.
Yes, sir. Accuracy of the temperature. Ma'am, actually, we measured the temperature from furnace. We have used hot muffle furnace. It shows temperature like 1350, 1400, 1450 accurately.
Anyway, similar question on that one.
Yes, sir.
I was about to ask you. 1400 degrees C, which type of a furnace you have used?
Sir, hot muffle furnace.
Hot muffle,
Just
was it a silicon carbide rod, or was it a infrared heating, or was it a supercathode?
Sir, I'm sorry, I'm not sure about it. Yes.
And do you measure the temperature externally also, because already the furnace is showing with the PID components of the temperature, right? But then what we do, normally we put a platinum rhodium thermocouple from the outside at that temperature, and then do we check? Do we check?
No, sir, I didn't.
So it should be checked, because that will,
Okay,
be
sir.
that will give us a reference value what they are asking for the estimation in temperature.
Yes, sir.
And moreover, while you are going to such a high temperature with the barium lightning, do you think, are you finding that your pellet is shrinking up to what level? The shrinkage happens to the high
Yes, sir.
temperature,
Yes, sir. Yes, sir.
and you don't need any oxygen into that.
Yes, sir, sir. Yes, sir.
You
I
use
didn't,
oxygen, right?
sir, I didn't measure yet, but I will include this in further research definitely.
You are how long doing the research?
Sir, I am in second year of my PhD only.
Second year, fine.
Yes,
You
sir.
can, these points can add.
Yes, sir. Yes, sir. I will add. I will definitely add.
Because having a very high dielectric hostel, and that too a short duration of 1400, 1450, 1450, that you have, the measurements are okay.
Yes, sir.
But the accuracy is to be
See.
seen properly.
Yes,
And
sir.
then you will be able to come to a conclusion.
Sure, sir.
A small question. What is the application you will be using this material for?
Ma'am, we have think about energy storage application, but we want to go for piezo catalysis, which is for water
You
splitting.
haven't decided yet?
Ma'am, I have decided, but I want to take the samples for that also.
Same to Deepika, then
Thank you so much,
nice
sir.
presentation.
Thank you, sir. Thank you so much.
Good afternoon.
Now,
Yes, sir, Piyush.
you are the next one.
Yes, sir.
Piyush Sirha.
Yes, sir.
Okay. So you are also from Central University of Haryana.
Yes, sir.
Title of presentation is already displayed, but polymer supported MO selenium.
Yes, sir. Molybdenum selenium dioxide.
Molybdenum selenium.
Yes, sir.
Uh,
PVDF
photo
HFP.
detector
Yes, sir.
with fast response and high detectivity.
Yes, sir.
So please proceed ahead.
Okay, sir. Thank you. In this work, we combine the optoelectronic property of MOSE2 with the flexible and ferroelectric polymer PVDF HFP for the flexible photodetector application. So I will walk through you the synthesis. First of all, no, it's okay. Brief discussion of my material, then the synthesis and characterization, and then the photodetector application part. So this is the why I choose the MOSE2. I am also working on the MOS2 also, but already they both have tunable band gap, and MOSE2 has a band gap lower than the MOS2. So I choose the MOSE2 for the photodetector application, and PVDF HFP. Why? Because this is the ferroelectric polymer, and it working well for the flexible photodetector application, and also help in the charge separation process because it is ferroelectric. And so first of all I synthesize the MOSE2 PVDF HFE polymer. First of all I synthesize MOS2 C2 using the hydrothermal method, and then mix this with the PVDF HFP polymer with the help of DMF. Then these are the XRD analysis of this synthesized sample. Okay, not removing. The blue one is the XRD of PVDF HFP and the peak position at the 20 nearby 20-degree angle showing to the beta phase of the PVDF HFP polymer, and the orange one is for the MOSE2 nanostructure material, and the peak at the different angles showing the different crystal line planes of the materials. And above one graph is the composite graph that appear the both peaks PVDF HFP also the MOSE2 materials that say that confirm the about the formation of the composites. And next the FSM morphology analysis also confirm the formation of composite, because and the MOSE2 structure also looks like in the third one slide, MOSE2 PVDF HFP in the PVDF, and also the composite purity confirmed by the EDS spectra that there is no extra peak present here, only MO, SE, F and C peak is available in this graph that confirm the purity of composite. Yeah, this is a photo detector study that I did in the CSIR NPL Dr. Govind Gupta sir lab, and here the graph curve linearly showed to the ohmic contact, and the power value also increased with the intensity or the power of the light, that showing that this is photo detector response, because we increase the intensity of the light then the current value also changes. So these are the IT parameters that check that show the stability of the device, and also the its repeatable cycle and its responsivity, its responsivity detect about the device that it is how it is sensitivity, and also the NEP, sorry, that is the noise. So sensitive, from the sensitivity we find that the how low or how low intensity laser it detect our device, or NEP so that the is low noise. So in our case high sensitivity and low noise, so it is our desirable result. That is about different detectivity that show it the increasing order, and this is the external quantum efficiency that we achieve in the 40% in our device. This is power dependent parameter that showing decreasing, that may be due to the ring combination or the trap equilibrium occur. So these are the conclusion of the device, that we successfully formation of the composite and then successfully make the composite with the and I characteristic photo detector application. And then yes, I adding one thing, our detectivity of this sample is less than reported papers, but our main aim is to make a flexible device and achieve a detectivity that is our successfully achieved. So these are the references for this work. Thank you.
Thank you. Anyone has got some question? Anyway, I have one question.
Yes, sir.
Molybdenum diselenide.
Yes, sir.
Did you check its stability for the months or what you are talking?
Yes, sir. We did the XRD V synthesis, and after 6 months, approx it take very much time. I send it sample for the XRD, then the result come. But we when do the photo detector application result, it takes 6 months approx. Then we again do the XRD, then its peak and position and intensity also same.
Same.
Yes, sir.
So that way your detection is being done same way.
Yes, sir.
Even after 6 months.
Yes, sir.
Good.
And our future plan is, sir, that we check the device after 6 months and with water condition also. We dip the device with water, and that also check the moisture condition. That in rainy season or any moisture season, our device how it working. That is our future work, sir.
That is good.
Yes.
Okay. Thank you.
Thank you, sir.
So you have synthesized MOSE2.
Yes, ma'am.
Okay, which phase?
2H phase.
2H phase.
Yeah, ma'am.
So why 2H?
That's not any main ma'am reason, because at the temperature 200 we synthesize the 200 degrees Celsius. At that temperature generally formation of 2H phase. For 1T phase we got below 200 and like 180 180
Which phase is better for your work?
no idea, ma'am.
Okay, thank you.
Thank you, sir.
Today's session is over. And yes, now everybody can move to the lunch.
Thank you so much. Um, Thank you so much, sir. Now, I would like to take a moment to express our gratitude to our respected session chair, Professor R.K. Kotnala, sir. Thank you so much, sir, for wonderfully chairing this session. We will now take a short break for lunch. Lunch will be served at the Samarth Guru Ram Das Auditorium that will be on the ground floor in the Jijabai Academic Block. And we will be resuming this session after just 10 to 15 minutes because we are already running late. So participants are requested to take your lunch, and then shortly we will be, again we are resuming in the same auditorium.
XPS. He has upheld research positions in France and Germany and is a recipient of Alexander von Humboldt Fellowship. With over 170 research publications, he has made significant contributions to advanced materials research, and he'll be talking on robust room temperature ferromagnetism in nano-dimensional MOS2 flakes by tailoring edge-terminated structures and point effects. I invite Professor Pankaj for his talk.
Good afternoon. I thank the organizers for inviting me to this conference. If you have the first lecture after lunch, then you are there, the chair is there, and maybe a few participants are there. So I hope more students will join, because I would like to deliver a talk which is understandable by all. So I thought that more PhD students will be there, but I hope they will join. Okay, so this is the brief outline of my talk. I will give a brief introduction and then give you a brief theoretical background, which is essential to understand the experimental results, which I would be presenting subsequently. And then there are three subtopics which you can see on this slide, where we have tried to control the defects in MOS2 and how these defects are related to ferromagnetism, which we observe in MOS2. That is what I will try to explain. So most of you are aware of the word spintronics, where what we are trying to achieve is that we are trying to achieve ferromagnetism in a semiconductor. So basically we are looking for semiconductors with ferromagnetic properties. So there are different ways people have tried for the last 10 to 20 years, I would say, where they have tried to induce ferromagnetism in semiconductors by doping. So they have gone for transition metal doping, and the problem with transition metal doping was that whether the ferromagnetism is intrinsic or it is coming because of the clustering of the transition metal, that was not very clear. So if you submit a paper where you say that I have observed ferromagnetism in a semiconductor by doping transition metals, you are always questioned, you will be asked several questions to really prove that the ferromagnetism which you are observing is really coming from the distribution which is theoretically predicted, and not because of clustering of transition metals. Thereafter, people realized that if you create defects, you may also observe ferromagnetism. This was initially termed as D0 ferromagnetism, because what people realize is that you do not require unpaired electrons in the D shell to see the ferromagnetism. So the defects, as you know, can be of different kinds. You can have a structural defect, you can have defects on the surface, you can also have a strain which you can see as a defect, and you can also have point defects like vacancies or interstitials. There's a recent review article which discusses all sorts of defects, but this review article focuses on oxides, not on other TMDs, etc. But those of you who are interested, it's a very good comprehensive review article. So here, what I'm going to do, focusing on MOS2, I will try to look at the defects which are growth induced. I will also try to tell you how the symmetry breaking gives rise to certain defects, which will eventually give you ferromagnetism. And I will also try to do these defects and also tailor ferromagnetism. Okay. So for this particular presentation, the material which we have is MOS2, and the techniques which I have used to create defects is ion irradiation, low as well as high. I would be presenting low energy results in this particular talk, but I can also create defects by annealing, and so these two methods are adopted to create defects in MOS2. Now, obviously the kind of defects which we are looking or which we will focus upon are the vacancies. So these can be sulfur vacancies in MOS2 or it can be molybdenum vacancy. And in addition to that, as I was telling you, that I will also talk about some sort of symmetry breaking which will give rise to ferromagnetism. Now, as I have already told you that there were several studies in which defect-driven ferromagnetism was studied in oxides. So these are some representative examples where oxides were used and ferromagnetism was seen coming only from the defects. There was no transition metal, nothing, but only from the defects people observed ferromagnetism. But later, around 20 years back, in graphene also people started to see ferromagnetism due to defects. Now MOS2, as you know, which is a recent material, and there are many, many applications. I will not go into that. But MOS2 also is a layered structure like graphene. So immediately people started to think that whether we can induce defects in MOS2 and see ferromagnetism. There are very unique properties which MOS2 has, like thickness dependent band gap. It is a layered structure, I have already told you. The interlayer interaction is very weak, van der Waals type, and they have a very strong covalent bond in plane. And the most stable phase of MOS2 is the 2H phase. Now, I would like to give you some theoretical background, because what we have done experimentally is to mimic these theoretical predictions and see how these theoretical predictions can be realized experimentally. Do they work or they do not work? That is what we are going to examine in this talk. So, one which is related So electrons get trapped there in that vacancy. Now, when these electrons are interacting with the molybdenum ion, which is adjacent to the sulfur vacancy, you have the interaction between the electrons. And when these electrons are spin polarized, it means that if this interaction gives rise to the parallel alignment of a spin, you may expect to see ferromagnetism. So that is the theoretical background behind it. So you have the spin interaction of the trapped electrons in the form at the sulfur vacancies, and you have molybdenum 4D ions, and the electrons there, they interact with each other, and what you have is a creation of a polaron, which is also known as bound magnetic polaron. So when you have several such vacancies, these bound magnetic polaron, they overlap with each other, and you have a long range magnetic ordering which gives rise to ferromagnetism. So this is one theoretical input which we have, and the other theoretical input is that if you have S-terminated structures in MOS2, what does it mean? That if you have a bulk MOS2, you will have a structure which is trigonal prismatic, but if you have an H-terminated structure, the coordination changes to octahedral, and what happens when you have two different types of coordination, that in one case you have the spins of the electrons which are paired with each other, you are not going to see ferromagnetism in this particular case, but in the other case you will have parallel alignment of electrons due to different crystal field splitting, and that will give rise to ferromagnetism. So what we have learned from this slide is that if I am having sulfur vacancies, I may see ferromagnetism, and secondly, if I break the symmetry from trigonal prismatic and make it to octahedral, once again I expect to see ferromagnetism. Another theoretical study which is related to the hydrogen interaction with MOS2, the DFT calculations have predicted that certain SH bonds, which are, if they are aligned in a certain direction, will induce a small ferromagnetic signal in MOS2, and also if the conditions are conducive, the hydrogen can interact with sulfur and get out at S2S. And therefore, if I am having S2S getting out of MOS2 matrix, I create once again a sulfur vacancy. So by interaction of hydrogen with MOS2, once again I end up getting a sulfur vacancy. So please keep these three scenarios in mind, that I need sulfur vacancies for ferromagnetism. I have breaking of symmetry which may give rise to ferromagnetism, and I can make hydrogen to interact with MOS2 which can also induce ferromagnetism. So as I said 2 minutes back, that we have tried to mimic these theoretical predictions in our experiments and see whether they are working or not. So there are many papers which are available, but none of these papers have examined all these three aspects together. And what you can also see from this table is that the saturation magnetization which people have reported is very, very small. It may not be very good from the applications point of view. So now I come to our results. So this is the first part where what we have tried to do is to control the morphology of the MOS2 nanostructures and see what is the effect of this different morphology on the observed ferromagnetism. So all these samples were grown by thermal CVD. The details are given there, and the paper I have already mentioned, those you will have all the details. So what you can see here is that by changing some of the parameters here, I don't have time to discuss all those things in detail, you have different mechanisms by which MOS2 is getting deposited on the substrate, and you end up getting very different morphologies here. So you can see some flower-like structure or some edge structures which are shown in these same micrographs. So what do we have? So let us concentrate. This is a zoomed version of the microstructures which we have got by changing the deposition parameters. So what you see, you have some sort of nanoflowers. You have in the second, the B shows you vertical nanosheets, and then you have horizontal sheets and slightly bigger horizontal sheets which I am calling as a thin film. And the typical thicknesses are also mentioned there. So this is the Raman data of this MOS2, all these four samples. And what you see here is that essentially you don't see much of a variation when you have different morphologies, but you do see a slight broadening on the Raman peak and also a shift. That suggests that somehow there is some strain which is there in the film. Let me admit that strain can also induce ferromagnetism, but this aspect we have not studied in detail. This is for now we will try to do, because there are now papers which talks about strain inducing ferromagnetism. Mainly theoretical papers are there. So I am not going to address the strain part, but that is what we see, that from the Raman spectra, not much change. From the XRD data, we find that there is some broadening and some shift. But as soon as you go to the MH curves, what you find is that for sample B, you get a very sizable magnetic signal. Now this signal 1.70 EMU per gram, even if I include the errors involved in the measurement, is much higher than what is reported in the literature. Now what is this sample B? The sample B is this structure. Now this structure, if you look carefully, has the maximum edge terminated structures. As compared to other morphologies, this particular morphology has maximum edge terminated structure. So I would like to remind you that what theory has predicted, that the edge terminated structure changes the coordination, which becomes octahedral, and that is conducive for inducing ferromagnetism. So this is what we see experimentally very, very clearly. Now this is the same data but recorded at 2 Kelvin. So you see slight increase in the saturation magnetization, and the Curie temperature of this is higher than the room temperature, as you can see. In the sample D, which was a thin film, we do not see any magnetization, and I get a diamagnetic signal. Now this is the FMI analysis, just to look at the composition. Why are we looking at the composition? Because by looking at the ratio of silicon to molybdenum, I would like to see if there is a significant change in sulfur vacancy. So what you find is that if I compare B with D, why am I comparing B with D? Because in B I see the maximum saturation magnetization, and in D is a diamagnetic signal. I find that the sulfur to molybdenum ratio is comparable, not much variation. But as far as magnetic properties are concerned, they are very different. B gives me a very clear ferromagnetic signal, whereas D is a diamagnetic material. Once again telling me that perhaps the edge terminated structures are playing a more prominent role in tailoring the ferromagnetic properties in this particular material. This is XPS. Once again to examine what is the situation as far as the sulfur vacancies are concerned. How do we find out the sulfur vacancies from XPS data? Just to look at the lower valence state, because what is going, this is for the students, what is going to happen if I am having a sulfur vacancy instead of having MOS2, I don't have a sulfur, then what I expect is that now molybdenum will go to the lower valence state, right? So this is what we see once again, that the lower valence state concentration or the percentage of lower valence state is not changing significantly. Once again telling us that perhaps the morphology in the form of S-terminated structure is playing a more significant role. So this is what I have summarized for part A. Now I go to the second part where I have now made hydrogen to interact with MOS2. I have used hydrogen ion irradiation, which we have used at IUAC, and also done annealing in the presence of hydrogen and see what happens to ferromagnetism. Once again, the process to make MOS2 was thermal CVD, and these are the parameters for irradiation, different fluences, and we have annealed these MOS2 in the presence of hydrogen at 100, 200 and 300 degrees Celsius for 1 hour. Once again, the similar kind of characterization analysis from first the XRD pattern. Once again, I am telling it again and again, we do see some broadening and some shift in the XRD pattern, which suggests that there is some strain which is there, which must be analyzed. We have not done that, and that can also cause some degree of ferromagnetism. That is what the recent literature is telling us. In the Raman data also, we do see some shift, once again suggesting that we have some sort of strain which is developing. Now if you go back and carry out MH plots, once again what you find is that you are once again able to get very sizable saturation magnetization. Even in the pristine sample, you have ferromagnetic signal which increases when you irradiate it with hydrogen. You can go up to 2.39, but if you anneal it in hydrogen atmosphere, this is what happens. You can get up to 2.7. In the last work I showed you, it was 1.7. Now it is 2.7. So in the presence of hydrogen, once again we are able to tune ferromagnetism, and I believe that the theoretical background which I presented initially is working here in the form of hydrogen interacting with MOS2 and perhaps creating the sulfur vacancies. So this is the data at 2 Kelvin. Now similar analysis with EPMA and with FESEM and looking at the ratios, and here what you see here, that with hydrogen annealing and hydrogen irradiation, you see a significant change in the sulfur to molybdenum ratio. So in this particular set of samples, along with the edge terminated structures, you see that the sulfur vacancies are also playing some sort of a role in tailoring the ferromagnetic properties. Once again gone for the XPS analysis, and now we see very clearly that the lower valence state of molybdenum is increasing significantly where we are getting larger ferromagnetic signal. So this particular part of study tells us that as far as hydrogen annealing or hydrogen irradiation is concerned, you have contributions coming from both edge terminated structure as well as the creation of sulfur vacancies when hydrogen has interacted with MOS2. I will not go into the details. We have also captured the valence band data where you see that you have molybdenum 4D states appearing as you make hydrogen interact with MOS2, which also tells the same thing, that you have creation of sulfur vacancies. Our colleagues have done DFT calculations for us, and they have shown that how the sulfur vacancy at the MOS2 edge or hydrogen absorbed at a certain angle on the MOS2 edge can give you very high magnetic moment. Please remember, I am not going to compare these numbers with the numbers which I have got, that they are very different. I was showing you numbers in EMU per gram. Theory people have found it in Bohr magneton. I can also convert it. They are not matching very well, but trend is there. What is being predicted by theory, you are seeing in experiments. So this is the summary of the second part, and now I will come to the last part. I will finish it in 5 minutes. Yeah. So this is our latest work, which is accepted very recently, which will appear very soon. Where once again what we have done is we have started with a thin film of MOS2, which is diamagnetic, and deliberately we wanted to create edges. So in the previous part of the talk, what I had shown you is that I already have edge terminated structures, morphologies of certain kind, and I have exposed that MOS2 to hydrogen, or I have exposed it to some other kind of treatment, maybe a annealing treatment, and got ferromagnetism. Here we will start with thin MOS2 films, around 20 nanometer thin MOS2 films, and then we have irradiated them with certain energy of argon ions. Okay. So what you see here is that you see very clear signatures in the Raman data. You can see these shoulders appearing, which are directly related to creation of sulfur vacancies. The same thing we can also see in XRD pattern, some shift, some broadening. Strain analysis we have not done. And you see a very sizable ferromagnetism appearing here. So we have gone up to 4.18. But what I want you people to understand and remember is that the thickness of MOS2, which I showed you in the beginning and which I am showing you now. Earlier I was showing you some 300 nanometer thick MOS2 film. This film is 20 nanometer. So it is very important that how many sulfur vacancies, that is how many point defects you create per unit volume, that also influences ferromagnetism. There is a critical concentration which is required to trigger ferromagnetism, and in this particular case our impression is that this film is thin, we are able to get to a very high number of magnetic moment. This is once again analysis of this. Now you see carefully, we started with something like this, horizontal nanosheets, and as you keep irradiating it, and finally in this position it is completely gone. It is completely, I would say, dismantled kind of a thing. The lower are the zoom views of what is happening. So here what I am trying to tell you is that we are deliberately trying to create edges. We are trying to break the continuous MOS2 film, and by doing that we have created vacancies, and also we have created edge structures, and both have given us a very large ferromagnetic signal. So here you find that you see a signature of creation of sulfur vacancies, and from the micrograph you see that up to a certain case you are able to create some edges. Once again, XPS also tells you that you have sulfur vacancies here. The shift in the valence band maxima in the valence band also tells you that you have creation of sulfur vacancies. So what we have achieved in this part of study is that we have created edge terminated structures and sulfur vacancies after ion irradiation, and that has resulted into enhanced saturation magnetization value, and these values are much higher than what is reported in the literature so far. And what we think is that the reason behind the enhanced magnetism is sulfur vacancies and edge terminated structure. So there is an interplay between the two, and both of them, as predicted by theory, is required to observe ferromagnetism in this particular material. So there is an interplay between the ferromagnetism induced by existence or creation of point defects and edge states, and our studies, if you just combine all the results, indicate that existence of edge states contributes perhaps more than the point defect, but this is a conservative statement. I would like to go back and check myself, and the detailed and systematic study of strain-induced ferromagnetism is required. We have not done that. So I would like to acknowledge Professor Shantanu Ghosh. We are working together. We is in the same lab. The entire data which I presented is from Sharmishta's thesis. She has already defended and gone.
Shashwata Bhattacharya is the person who has carried out the DFT calculations. IUAC, where we have done some part of irradiation studies, and also in SZDR Germany, we have carried out some irradiation studies, and we got some financial support from DSC, and we have used many central facilities of IIT Delhi. Thank you.
Thank you, Professor Pankaj. That's an excellent talk. Now the session is open for questions.
Please.
Sir, in the last part of your presentation, you showed that the sample D, it was in the form of thin films, right?
Right.
It was in the form of thin film, right?
We started, yeah, I'm calling it a thin film, but basically these are horizontal big nano sheets. Yeah. Okay, and what we have done by radiating them, we have broken these sheets into small pieces.
Yeah. That's
by
crystal structure still remains same.
yes, it does. But with the extreme irradiation thing, it is not the same. It is still, crystallinity is lost. So I will tell you. So when we come to this particular position, the highest irradiation thing, the crystallinity is lost. But up to this point, we are still getting 2H, the most stable crystal structure of MOS2. Let me also tell you, since you have asked me this question, that there is a metastable phase in MOS2, which is 1T. And there are theoretical studies in which say that if you have 1T contribution in 2H, that will also give rise to ferromagnetism. So it is a theoretical this thing. So perhaps our paper went to a third person. So he was after us, or he or she was after us to prove that it is indeed 2H and there is no 1T mixture in this. So that is what we tried to do.
So in all your samples, the Raman data looks almost
Yes. So it tells me, okay, macroscopically it looks very similar. We do not see any significant change. But if you look at it minutely, you will find that there is some shift and some broadening. And as I said repeatedly, that tells me that there is some strain which is also getting tuned. So if I am carrying out some post-treatment, whether it is annealing or whether it is irradiation, it is inducing some strain inside the film. And then strain can also give you ferromagnetism. These are recent theoretical works, and we have also seen, not in MOS2, but in some other material. So that has to be examined. So answer to your question is yes, macroscopically there is not much change, but if you look at it minutely, there are changes.
so the minor changes that you're talking about in Raman studies, it's just for my understanding I'm asking this question. Does it mean that the octahedral structure that you have shown, you said that this system hasn't changed in the samples, right? So the octahedron is getting into some kind of vibrations and it is being reflected in the minor changes in the
Yes, so if you just see this last example, if you compare this Raman data with the previous sets of data of Raman, here you see very significant change. You see this huge shoulder coming here, 2 LA peak is appearing, and also a shoulder. I don't know whether it is also coming at this position. If you refer, I am not an expert in Raman spectroscopy, but when I looked at the literature, it is said that these are all related to creation of sulfur vacancies.
Kind of asymmetric.
Asymmetric, yes, asymmetric peak, which perhaps is also related to what you just now said, that you have now different kinds of vibration which are happening because of the symmetry breaking.
But it's still maintained.
It is still 2H. It is predominantly 2H. So even in the H-terminated structures, I need to do something which is very selective to see the octahedral symmetry. But overall, macroscopically, what you get is a 2H kind of structure.
Any more questions? I have a small query. Why is ferromagnetism important in MOS2?
Okay, it is basically.
So what's the significance of the study?
The significance is what people thought 20 years back. They would like to have semiconductors with magnetic properties. It is as simple as that. So if I have semiconductors, they have huge applications. Yeah. But if I am having a situation where you have spins also, which is giving rise to ferromagnetism, then the devices which you can think of are enormous. The form of
Spintronic
spintronics.
applications.
Yes, basically spintronics.
Thank you. I think with this we thank Professor Pankaj. Thank you so much.
Now I request our esteemed chairperson, Professor Kanupriya Sasde, to kindly felicitate Professor Pankaj Srivastava as a token of our appreciation by presenting him a pot and a memento.
Our next speaker is Dr. Pawan Kulria from JNU Delhi. I invite Dr. Pawan Kulria for his talk. To introduce him, he currently serves as Dean School of Engineering and Professor of Physics at JNU and has previously worked for 17 years as Scientist F at IUSC New Delhi. He is a recipient of the prestigious Fulbright Nehru Postdoctoral Fellowship with over 170 research publications, 4,200 plus citations, and an H index of 36. The title of his talk is Materials Engineering of and Vaccines for Advanced Optoelectronic and Sensing Devices. Dr. Pawan Kulria, you are invited for the talk.
So thank you very much for nice introduction, and good afternoon to all of you. And I'm also thankful to organizer for inviting me in this prestigious conference. So today I will speak about a few of our results related to materials engineering of the machine for advanced optoelectronics and sensing device applications. So you know that machine is a 2D materials, and it is recently discovered. So before going that, I will briefly introduce the area that we are working. So broadly, we have expertise in the area of, I think this will not work. Okay.
It's an LED, so.
LED, yeah. Yeah. So mainly we are working in 3 areas. So broadly, that is, we are designing some material. That material can be used for disposal of high-level radioactive waste that is coming from the nuclear reactor. So in that one, these are the ceramic material that we call as a nuclear material that can be used for disposal of radioactive waste, as well as these material can be used for design of nuclear fuel for next generation reactor. Then another area that we are working is high entropy alloy. Again, purpose of these alloys, again, that can be used for, again, nuclear reactor application, particularly advanced nuclear reactor. And you might be aware that yesterday there was a good news from the atomic energy, and we have successfully installed and critically has been achieved by a fast breeder reactor. So particularly because you are the undergraduate student, most of them. So our nuclear energy program is started in 1960, and till now only 10 gigawatt electricity that we have produced. And our vision is that by 2047 it will increase 10 times. So that way you can expect how many opportunities that will be created. And by 2070 we are going for net zero emission. So all the energy that we are going to produce, that from the nuclear energy only. And this fast breeder reactor, that is the second step in that one. We have 3-stage program. So I will advise all the students, please go and read about what is this fast breeder reactor, why it is important, and why Prime Minister has specifically tweeted in this one. Okay. Then there is another area that we have recently started, that is a 2D material. And again, aim of these 2D material, because whatever material that we are designing, they are costly material, and we have plan like that whether we can do coating of these 2D material on these alloy so that we can save some cost. And in the meantime, we have done some other testing of these material, particularly for the sensing application. So today I will discuss few of the results related to the optoelectronics application of these material as well as sensing of these material. So today's talk mainly will be focused on MXene. So MXene is basically it is synthesized from the max phase. So max phase it was discovered in 1996, and this max phase is particularly it is MAX. So M is early transition metal that you can see in red color, and then A is group A element. So this max phase, I think more than 500 different max phase has been discovered since 1996. Then what is so special? So in 2011, these two professors, Yuri Gogosty and Michel, they have discovered MXene. What they have done is that from the max phase, that you know that this hexagonal structure is there. So in max phase, if by some mean, if I can remove a group element, okay, so then this material is showing unique properties. Okay, so there could be n number of ways by which we can able to remove it. So in our lab, we have synthesized this MXene by two methods, and we have controlled the process parameter. That thing that I am going to discuss in this talk. So as on date, we have particularly focused on T3AlC2 MXene, but as on date, I think more than 50 MXene people have discovered it, and each MXene is showing different type of application, as per depending upon the requirement. So why this MXene is important? Because this MXene is a 2D material, and it is showing unique property like they can be used in electromagnetic shielding. You can able to control the band gap of the MXene depending upon what type of transition metal that you are going to take it. Then they are also showing good absorption and desorption behavior, and they have abundant active sites, so that's why it can be used for gas sensing application. They are showing excellent electrical and mechanical strength, and they are also in hydrophobic nature. So they are showing all good properties, and that's why all the area of the physics and chemistry people are exploring it. And these are the key area, like they can be used in the energy storage as well as catalyst, optoelectronic application, sensor, biomedical, and even wastewater treatment. So please, we have published the review article on this advanced material. So I will advise student, you can refer this article and more detail what different type of application and what different ways by which MXene can be synthesized, that detail can be found. So there are two prominent methods for synthesis of the MXene. First method is etching method. So first I will discuss this method, how we can synthesize the MXene by etching. So this is a very simple method. Only thing is that we have max phase, and by some mean we can able to remove the A layer. And most appropriate is we can take any strong acid, we can take it, and with help of the acid we can able to remove the A layer. So we need to do sonication and all these things. So this is the simple procedure. Like in this case, we have taken lithium fluoride and HCl as a acid. Then we add max powder in this one. Then we have sterilized it. After that, we have washed it. Then we done centrifuge. And most critical part in this case is the pH, because in this case, pH is supposed to be around 3. And you can go to n number of paper, but you will not find what is the exact value of the pH. And that is the key issue in this case, because when we try it, in most of the paper, everyone will, even we are also reporting like that, pH value will be around 6 only. But if slightly we will change the pH value, as a result of that, it will give the mixed phase. So that thing you have to do by your own experiment, and then only you can get it. Then after that, we will get suspension, then we will do the sonication. After that, again, we will do the centrifuge. And depending upon the what is the RPM of the centrifuge, that will again decide the property of this mixing. So in this case, this is primary tool usually that we will do any material is XRD. So that black data that you can see, this is a X-ray diffraction data from the max phase. And critically, we are looking a peak that is appear around 10 degree 2 theta, that is 002 plane. So in max phase, it is around roughly around you can say around 10 or 9.8 degree. But as we have done sonication and different centrifuge speed, so as a result of that, this 200 plane will be shifted toward lower angle. So that you can see, depending upon the speed like that, you can see at 7000 RPM peak position is around 6.5, and then we further increase to 10,000 RPM, then it is 6.1. So it means like that peak is shifting toward the lower angle, means there is a lattice expansion is there, or some strain is induced in this case. But another important thing is that in addition to this peak, you will not find any peak. So that way we can say like that this is a single phase material, and whatever aluminum is there, that we have completely etched it out. To further confirm this thing, because from X-ray diffraction data, it will give only long range ordering in the sample. So if we want to know the short range ordering and or disordering, so for that we can do the Raman spectroscopy. So in case of max phase, E2 G vibration mode of the titanium should be appear around 198, that is exactly coming at the same value. And when it is converted to the maxine, then this peak again will be shifted to the around 142 centimeters. So whatever data that is reported in the literature, exactly that same we are found in this case. So for further confirmation of that whether aluminum is etched out or not, so same we have done scanning electron microscopy, and EDEX is attached to that. And with EDEX that you can see like that max phase is containing around 20 percentage of aluminum, and in case of the maxine it is 1.9 and 0.29. So that way, by just controlling the RPM like centrifuge speed, we can able to control the or we can able to remove the aluminum from this one. Then these are the again SEM images, and from there you can see like that layer structure can be clearly seen from that. So on the basis of that, we can say like that we have synthesized a single phase maxine by using this etching method. Then after that, because we want to propose this material for photoelectronic application, so we have done photoluminescence studies of this material, and then this data we have fitted by using this by exponential model. So TRPL data is there, and from there we calculate the decay time. So decay time for in this case is order of 5.1 and 5.35 nanoseconds. So if you will compare with the decay time in case of the rare earth element or like, that is order of the micron. So in this case, micron order 2 you can able to reduce order of the nanosecond. That is a really large change in the decay time as we can go into the material. Then in this method there is a problem because we are using the strong acid, and that is not advisable. So there is another method, that is a hydrothermal method, and we have synthesized maxine by using this method also. So in this case, you need to use autoclave. So we take NaBFO salt, and we added HCl, and then maxine powder we have taken it. Then we sealed this powder in the autoclave, put it at 160 degrees centigrade for 8 hours. Then we wash it, and finally we collected the sediment, and then again we have treated at 75 degree, and then we got the maxine powder. And then we also collected the supernatant, that is a solution, and that solution we use to drop cast, and we make the thin film of this thing. So we characterize powder as well as the thin film of the maxine. So in this case, if you will compare the XRD data of film prepared by using etching, and in this thing you can see like that peak intensity is clearly distinct, that you can see it. So that way it is clearly showing like that in hydrothermal method quality of the crystallinity in the XRD is better as compared to this thing. So particularly when we are talking about the sensing application or in any electronic devices, crystallinity is playing very important role. So that way, just by changing the method, we can see like that crystallinity is improved a lot. And in addition to that, same in the Raman data again, because it is giving the short range ordering, still you can see the intensity is quite good as compared to this thing. So that way, if we compare these two methods, then clearly it is indicating that hydrothermal method is good as compared to the HF method that we are using. Then this is the data again from the scanning electron microscopy. So there it is like again layered structure that can be clearly seen from this one, and aluminum has been completely etched out in this case, like it is less than 0.2% or something like that. Then we have, to further confirm this, we have done transmission electron microscopy TEM of this data, and from TEM again you can see clearly diffraction pattern is also there, so clearly polycrystalline nature of the film, as well as you can see layered structure of this one can be clearly seen. Then we done the optical properties of this thing, and band gap we calculated it, and band gap is order of around 2.8 and 2.03. Then to compare the result of earlier data, we have done TRPL in this thing. So if you compare the decay time of this method as compared to earlier method, so in this case decay time is, in this earlier time it was around 5, but here you can see around 2.8 nanometer. So by just changing the method of the preparation, we can able to control the decay time of this material. Then this was the thoroughly we single phase machine we prepared it, and then one of our student is working on nanoparticle, and then he got the idea like that why we cannot add the gold or some noble nanoparticle in this thing, and then can how this material will be behaving. So then we, by some chemical route, we prepare the nanoparticle, and during the synthesis process we add the nanoparticle, and then same we characterize it. So in this case, G100 and G50 like two set of the nanoparticle, like nanoparticle size is 100 nanometer and 150 nanometer. These nanoparticle we added it, and then again we thoroughly characterize it. So again there you can see like that decay time, if you will compare with earlier two method. So in case when we added the gold, then again we can further able to reduce the decay time like around 3.0. So that way you can able to control the decay time either by changing the process parameter or by incorporating the noble metal nanoparticle. Although I am not discussing these results, but recently we also tried same thing with the silver nanoparticle also like that. So by changing the doping different size nanoparticle, you can able to control the decay time of this thing. Then thoroughly characterized machine, where plan is to make the photodetector out of that. So you know that photodetector is basically it can be used to prepare the it is optoelectronic devices, and in this case optical signal we are converted into the electrical signal, and it has various applications like in optical communication, image sensing, in biological detection, night vision, and many other applications it can be used. So although pure machine can be also proposed as a material for the photodetector, but these are the some issues like that it has a less photocurrent response to the optical signal. So sensitivity will be very low. Then it has a high dark current, and metallic conductivity is very high, and high scattering coefficient. So due to these issues, and theoretically people have proposed like that why not we can have some heterojunction. So machine and semiconductor heterojunction, if we can prepare it, and then there was some result like that people have proposed like we can try with the like machine gallium nitride, machine titanium dioxide, machine silicon, MOS2, and machine zinc oxide. So these are the few theoretical as well as experimental result people have proposed it. So in our case, we have taken this MOSE2 thin film. So this thin film we prepare by using simple electron beam preparation. So we took the MOSE2 powder, and then we prepare the thin film of MOSE2, and then we thoroughly characterize it. And we got the single phase, and again we characterize by XRD as well as from the Raman, and these are the SEM data. After that, we prepared the device of this thing. So we took P-type silicon, and then we grow a oxide layer of this silicon dioxide around 13 nanometer. After that, we prepare MOSE2 film by using electron beam evaporation. And then by spin coating, we have Maxine powder, Maxine solution. So with the help of spin coating, we prepare a thin film of the Maxine, that is roughly thickness was 13 nanometer. So this was the Maxine MOSE2 photodetector, and that photodetector we further characterize it. So first thing is that we need to verify what is the electrical resistance of this. So simply we done the whole measurement, and then carrier type in this one is N type. Concentration was 4 into 4.73 in 10 to the power 20 meter square, and whole mobility and rest of these parameters there. Then we done the IV characteristic of this thing. So this one is under the dark and photocurrent. So this is showing like a diode response that you can see it. We illuminated with intensity of 372 nanometer at a power of the 4.4 microwatt, and very good rectification response that you can see in this case. And then these are the some other parameter of any photodetector, because we need to compare with the other material. So these are like responsivity, external quantum efficiency, noise equivalent power, and specific detectivity. So these parameter we calculated, and then we this is the responsivity. So in case of responsivity, that you can see like that, it is as we expose it, so it is increasing in the UV range with starting from the 270 nanometer, and then it attained maximum of around 159 microampere per watt at a wavelength of 372, and after that it start decreasing. So from these data we calculated these parameters. So in this case, responsivity of the detector is 159 microampere per watt, external quantum efficiency is 53%, and noise equivalent power is 10 to the power minus 9 hertz, and specific detectivity is 2 in 10 to the power 7 zone. So thoroughly tested with, and then to explain the result, we propose this mechanism, because these are the two materials, and when we combine these together, then Fermi level will be aligned in this case. And then we apply like positive ice and negative ice. So depending upon the number of carrier, that barrier height will be changed. So when we apply the forward wise, then you can see like that electron from the MOSE2 will be transferred to the Maxine, and in reverse wise other is going to be happen. Then we expose to the like light. So more detail that about the sensing mechanism that you can see from our paper like that we have published in IEEE sensor. So this is the one result that we have discussed on the Maxine, and now we are in collaboration with Siri Pilani. We are fabricating this detector, and then we will go for further testing and all these things. Then another area application of Maxine that is because, as I mentioned, this material can be used for various applications. So we tested for NO2 sensing of this thing. So this sensing setup, it is available in our lab. We have indigenously designed like that. And then one preliminary experiment recently we conducted on this thing. So in this one is that, as I mentioned, is pure Maxine. We have taken it, and then we tested the sensing response at different temperature, like at 50 degrees centigrade. And then two set of nanoparticle that we have added, like silver nanoparticle coated with the Maxine, and another in the gold nanoparticle, whatever that data that I already discussed. So in this case, if you compare the sensitivity, particularly when we expose to the different concentration of the NO2, so you can see like that as compared to the room temperature, at high temperature sensitivity is increased across all the concentration that you can see. So roughly it will increase like 2 times when we go to the high temperature. But metal nanoparticle, in that case, even it will further increase like that. In case of the silver, it is increased like 2.5 times. And in case of the gold, that you can see like it will drastically increase, like roughly you can say like 12-fold increase in the sensitivity when we added the gold nanoparticle. But this is the unpublished data, and more experiments that we are doing it, and detailed study that we will publish it. So with that, I will summarize my talk. In this talk, I have discussed synthesis of the MXene by two methods. And then we fabricated MXene MOSE2 heterojunction as a photodetector. And from TRPL data, we observed like that when we incorporated the gold nanoparticle, then as compared to the pristine MXene, decay time is reduced. And then we also, I have explained some of the parameter of the high responsibility, high external quantum efficiency, and specific detectivity of this detector. And most important thing is that in this technique, we have not used any high-end equipment or like that. Even at college level, like you just need a autoclave and some beaker and all these things. Even at your college, you can synthesize this type of sample and you can able to prepare this type of material at your lab. So with that, these are our collaborators. So most of the work that I presented in this one is MXene is done by the Ankita Rawat. So right now she is working as an assistant professor in Government College Uttarakhand. And some of the result right now that Gaurav Rajput he is doing in this area. And we also got this work is funded by ANRF this. And again, JNU pair, we also propose this work and we want to develop a photodetector in this case. So with that, thank you very much to all of you.
Thank you, Dr. Pawan, for an excellent talk. The session is open for questions.
Yes, sir. It's my honor because first time. So I must tell you that I have done MTech from IIT Delhi, and I think Professor Srivastava was the first person who taught at material science in 2001. So he introduced me to this area of material science. So it's my honor to present before you. Thank you, sir. Yeah.
Very interesting talk. So as far as the decay is concerned and the last result which you had presented,
Yeah.
Both were significantly influenced by this gold decoration.
Yes, sir. Yes, sir. Yeah.
Do you have some understanding about it? Why is it happening?
So mostly, sir, if I will compare with the structural data, so from XRD, because I am expertise of XRD, so from XRD you can see even if you compare the peak intensity all these things, there is clearly intensity is increasing. So that is indicating like that ordering of this material is increasing when we are incorporating the nanoparticle. And most likely is that because there are some free bonds are there when we are incorporating the nanoparticle. So then these nanoparticles, they are helping to rearrange the atom, and that is increasing crystallinity, and as a result of that we are getting, I think. But another thing is that in this case we have not done this UV visual spectroscopy. So it is quite possible like that there is change in the band gap also like that. So then we can give more indication like that. One structure point of view, we are sure like that crystallinity is improving as we are adding more nanoparticle. But in addition to that, it is quite possible there is a change in the band gap also like that. So that is two idea that we have.
Thank you.
Yes, sir. Thank you.
Any question from the audience? Then I would have a question.
Yes, ma'am.
A few questions actually.
Yeah, definitely.
One is related to just what Mr. Srivastava asked, that you said it becomes more crystalline by decorating the gold. So how would a more crystalline material be more better in the performance?
Yeah, because if, for example, because we are detecting the light, okay, so if some defects are there, then it is quite possible light will be trapped in these defect site.
I'm more interested in sensing, gas sensing.
Achha, gas sensing, okay.
Yeah.
So in gas sensing, because we have done only preliminary result in this one, only one experiment we have done it. But still is that because in this case sensitivity is increasing.
Yes.
And we are adding metal nanoparticle. And in case of the metal nanoparticle, you know that the surface area will be more. Number of atoms at the surface will be more. So then surface area will be then there will be lot of absorption site will be more at the surface. So that way, if we can increase the surface area, that way sensitivity is expected to be increased. So that could be the reason for that, because we are providing some site. At that site, gas can be absorbed there.
And regarding the photodetectors,
Yeah.
we are making a layered structure of amexine and the semiconductor.
Yeah, yeah.
So what are the type of semiconductors, like P-type, N-type, both of them?
From whole effect, we found this is N-type.
Both of them?
Yeah.
Amexine as well as the semiconductor?
Yeah, yeah.
And what about the band gap? Are they direct or indirect?
Band gap is direct band gap, and then
Both of them?
both about MOST, I don't know. For Maxine, it is a direct band gap. MOST2, I don't know.
Because a photodetector needs a direct band gap
Yeah,
material.
yeah.
So I
What
was
do we get?
curious to know that.
Because MOST2, I have not characterized, so I don't have any idea. But Maxine is a direct band gap, and band gap of this one is around 2.8 nanometer electron volt.
And this is a hydrothermally synthesized amexine? Because
Yes,
you
yes.
said you use two methods to synthesize.
Yeah, yeah. Second one is
The
hydrothermal.
second.
Because hydrothermal is giving better result. Although controlling the pH in hydrothermal is difficult. So we can easily synthesize the
It's
Maxine by.
less toxic.
Yeah, less
The
toxic,
first
but
one is very toxic.
very toxic. But synthesis method is easy, because main role in this case is controlling the pH. So if there is slightly, even in second decimal pH, we will change it. So as a result of that, a lot of impurity peak will come. So I think in this case, my student have the around, I think, 50 time synthesis, and after that she got the single phase. And even note, you will not find a single paper, and in that one people are reporting what is the exact pH. Most of the time we are reporting pH will be around 6, but 6.1 or 6.5 or 6.05, that is the main issue in this case. So if pH is slightly changing, as a result of that, impurity peak will come, and then you will not get anything out of that. But some time like that, there are some application, particularly when in case of the battery. So I visited last week in sub lab. In that lab, if some impurities are there, that is good for the batteries. So they don't want crystalline Maxine. They want like amorphous Maxine. So there was no peak in their XRD data, and then they are getting very good result in the batteries. But depending upon the application, yeah. So in case of photodetector and gas sensing, we need a highly crystalline single phase Maxine. But there are some other application in that one, even amorphous Maxine can be also useful.
Thank you so much.
Thank you, ma'am.
Thank you.
Now I would like to invite our respected chairperson, Professor Kanupriya Sasde, to kindly honor Professor Pawan Kalaria with a token of our gratitude by presenting a potted plant and a memento.
Okay, so I invite Dr. Nisha Bala for the first oral presentation. She's from Daulat Ram College, DU, and the title of her presentation is Annealing Effects Under Different Atmospheres on the Structural, Growth and Magnetic Properties of NIO Nanoparticles.
Thank you, ma'am. Good afternoon, everyone. So I am presenting a topic title is annealing effect under different atmospheres on the structure, growth and magnetic properties of nickel oxide nanoparticles. This is the brief outline of my talk. Firstly, I will introduce and then the synthesis and characterization techniques and how annealing effects on the microstructure and magnetic properties of the nickel oxide nanoparticles. Further, I have studied the phonons as a probe of the magnetic ordering of NIO. Magnons is also a useful probe of the magnetic ordering in nanocrystalline nickel oxide and stoichiometry, and then finally conclusion. Firstly, I will introduce what is NIO, the basic properties of nickel oxide. Nickel oxide is a transitional metal oxide p-type semiconductors. It crystallizes rock salt structures and having a wide band gap 3.6 to 4 electron volt. Nickel oxide is also showing the ferromagnetic to antiferromagnetic transitions when it is from bulk to nanometric scale, and also shows the size dependent properties of ferromagnetic to antiferromagnetic spintronics. It is also a benchmark of the strongly correlated systems, and one of the important property is the color. Color is showing the stoichiometry of the nickel oxide nanoparticles from lower annealing to higher annealing temperature. And one is the main topic of the magnetic properties of NIO, which has been influenced from the literature survey. Microstructure size, morphology and stoichiometry has been modulated by the synthesis and processing protocols. Phonons and magnons is also used as a probe of the magnetic ordering in nickel oxide nanoparticles and has been determined by the Raman spectroscopy. This is the scope of the work: chemical synthesis, how thermal annealing affects the different properties, and Raman spectroscopy shows the antiferromagnetic to ferromagnetic transition, and then spin phonon coupling in nickel oxide nanoparticles, and then size dependent magnetic properties. I have done the synthesis by using sol gel method. This is the the left side is the basic technique of the sol gel method, and the right side, which I have chosen, the nickel acetate tetrahydrate as a precursors plus methanol, and continuous stirring at 60 degrees Celsius. After that, the gel has been formed, and after that I did oven drying, and the green color nickel hydroxide powder is formed. After that, I did annealing in different temperature, time and different atmosphere. Finally, the nanocrystalline nickel oxide powder has been formed, which we can see here from black to green color. These are the characterization techniques: X-ray diffraction, transmission, electron microscopy, SOED, TGA, Raman spectroscopy and VSM. Selection of the annealing conditions. Actually, I have started different annealing atmospheres: argon, nitrogen, oxygen and air. But in inert atmosphere, we can see that only the sizable nickel phase is observed in the nitrogen and argon annealed samples. Though on the basis of these, I have chosen only air and oxygen annealed samples for further studies. These are the thermogravimetric analysis of the as prepared and 400 air annealed samples. We can see that the as prepared samples, the two stages of the weight loss occurs. First peak is the amount of the oxygen release, and the second broad peak is the nickel hydroxide. And after that, we can see after annealing at 400, this is a complete indication as our sample is showing the as prepared nickel hydroxide piece is suppressed and the complete NIO is formed here. Further, I done the XRD of the nickel oxide nanoparticles and studies the effect of thermal annealing. The comparative oxygen and air annealed samples we can see here. The nickel 400 to 600 oxygen annealed samples, we can see a sizable nickel phase is observed, although in air annealed samples the nickel phase is not observing in the XRD pattern, and the peaks has been matched with the standard JCPDS patterns and shows this is the phase center cubic structure of the NIO. And after that, I have calculated the crystal size and strain by using Williamson-Hall plot method, and we can see how's the size varying with temperature, and the strain is also varying with the annealing temperature. After that, I did microstructure analysis by using retrieval refinement by using foolproof software, and we can see that in these air annealed samples, the peaks are fit by the pseudo-Weigelt functions, and the backgrounds has been done by the linear interpolating polynomials. After that, proper good fitting and the goodness of it is around 1.4 to 1.5. The lattice parameter also calculated from the WS plot method and also from the readable refinement, and both are showing the same trend, how the lattice parameter varying with the crystallite size. This is also same for the oxygen annealing temperature, but we can see that at 400 degrees Celsius it is showing a droppage, and this is mainly occurring a sizable nickel phase is observed. On the basis of this, this is also showing a higher magnetic behavior, which we will discuss in the coming slide. How size varying as a function of annealing in the transmission electron microscopy. At the 400, both the temperature are showing, and atmosphere are showing the spherical particles, but if we are increasing it goes from spherical to hexagonal. And then after the basis of, I have chosen some particles, some parts, and the average size has been calculated and which has been shown in the histogram. Though color, I have already discussed, color is also indicator of stoichiometry. We can see here at the 400 to 1200 degrees Celsius. Firstly, as prepared sample is around light green color, and then at 400 we can see this blackish in color, and then 500, 600 we can see it is showing grayish black, and then after 1000 degrees Celsius we can see it is greenish gray, and then 1200 it is the pure form of nickel oxide, and the green color is also when we can purchase from the market, the original green color NiO, pure form of NiO is the green in color. And we can see in the 400 oxygen anneal samples, these are almost black and grayish black. And the nickel and oxygen vacancies, which has been calculated from the ADS spectra, is also varying with the annealing temperature. Then Raman spectroscopy. Raman spectroscopy is a light matter interaction. This is the basic slide, how electromagnetic radiations interact with the material, and it can be absorbed, transmitted, and scattered. And this is the basic form of the Raman spectroscopy. And this is also how phonon and dispersion relation is showing here, the acoustical branch and the optical branch, because in my Raman spectroscopy there is LO and TO modes are observing here. That's why I have included the basic slide here. And this is also showing phonons, means the magnetic and order induced effect. And this is the literature based survey. On the basis of this, I have investigated how we can study by using the Raman, because the right side graph is based on the elastic scattering data. This is the magnetic order induced effect from the optical phonons. We can see that there is LO and TO phonon in the 400 to 600 range. Although these phonons are almost forbidden in the rock salt crystal structure of the bulk NiO, but it can be observed due to some effects. And the lattice distortion also. A broad peak is also observed at 1 phonon plus 1 magnon is attributed to scattering of the 1 phonon and 1 magnon by the Brillouin zone center. After that, I have taken the zoom-in graph and analysis done. The TO and LO modes varies with the crystal size, and how the TO and LO splitting is showing here. And this data has been matched with the elastic scattering data, and Huching et al. Also reported by the same. This is the wavelength dependent spectra, how the different wavelengths showing the different spectra. We can see here we have used 488 and 514 nanometer laser off resonance and near resonance, and we can see that 488 nanometer laser, the TO splitting is observable, and we can see 325 nanometer, the only TO peak is observable, not splitting is observable here. this is the left side how the magnons are showing the magnetic effect here. The 2 magnon peak is sharply increasing with the increase in the crystallized size, because this is showing the behavior from ferromagnetic to antiferromagnetic, because in the lower temperature there is some defects and the nickel phase is observed. That's why the lower annealing temperature, the 2 magnon peak was totally suppressed, and we are increasing the temperature and the size is increasing and the 2 magnon peak is clearly observable. These are the magnetic hysteresis loop. This is also a sizable loop. It is shown here that lower annealing temperature is showing the higher ferromagnetic behavior, but when we are increasing and showing the 2 magnon peak is observed, after that it goes from ferromagnetic to antiferromagnetic behavior. This is the comparative data of the air and oxygen annealed samples. We can see that 400 is the oxygen and black one is the oxygen and the red one is the air. Black one is showing the higher magnetic behavior and higher saturation behavior, because at 400 air to 600 the nickel phase is observed. On the basis of this, I have confirmed the lower annealing temperature when the persistence of nickel phase is observed, and it is showing the ferromagnetic behavior when the nickel phase is suppressed and it goes from Ni to NiO, and it is showing there is a transition from ferromagnetic to antiferromagnetic behavior. And this also has been done by using the large fit and showing here the magnetization behavior by using the different applied field, and shows how it is varies with the different applied field. And the right side we can see magnetic saturation, coercivity, retentivity, how varies with the annealing temperature. This is the summary of my work. The nickel oxide was synthesized by the chemical method and studies the structure, optical and vibrational properties, investigated the annealing effects in different atmospheres, and the crystal size increases with the increase in the annealing temperature. Magnetic order induced effect also studied by the help of Raman, and the magnetization measurements also shows the ferromagnetic with large coercivities and magnetization with decreasing size be shown to be due to the thermoinduced contribution. This is the future scope. I would acknowledge my supervisor, Professor Shamarath, for her kind supervision, guidance, patience, and attention to detail. I would also acknowledge to UC, Department of Physics and Astrophysics, University of Delhi, for their cooperation and support. Thank you.
Thank you, Dr. Nisha, for your talk. Now session is open for questions.
Yeah, so thank you, Nisha. So can you go to one of your slides that related to the Raman spectroscopy? In that one you have shown Raman data is changing with the size from 100 nanometer to, yeah, this one. So in this one, as you can see, like from 100 nanometer to 30 nanometer. So as we change the size, this peak broadening is there.
Yes, sir.
So what is the reason for that? Like,
sir, at a lower temperature, the size below that there is no peak is observing, and after because this is data is around 30 to 100 nanometer.
For example, like there is a peak around 1100 centimeter inverse in this one.
Yes, sir.
So there is no peak, like just broader ramp is there.
Just broader, and it goes to
100 nanometer. There is a clear peak is there.
Yes, sir.
So why peak intensity will change as we increase the particle size?
Sir, the defects has been reduced on the basis of this. The broadening is also reducing.
And peak shift is also there, I think.
Sir, there is a peak shift. Little bit peak shift is showing here. Sir, I have studied on the basis of size and crystallinity. If the crystallinity is increasing, then the peak shift and the broadening is decreasing.
Okay, thank you.
Okay, sir.
With no more questions, we thank Dr. Nisha for her presentation. The second oral presentation is by Ms. Sonia from Netaji Subhas University of Technology, New Delhi. Our title of presentation is Adsorption of Methylene Blue by HKUST1 MOF synthesized using room temperature and solvothermal methods.
Good afternoon, good evening to everyone. Myself Sonia from Netaji Subhas University of Technology, Dwarka, New Delhi. I am pursuing my PhD Dr. V. Namarta Singh. So the title of my presentation is Adsorption of Methylene Blue by HKUST1 synthesized using room temperature and the solvothermal methods. So these are the outlines of my presentation. Firstly, I will discuss the introduction of the metal organic frameworks. Next one is the various properties and application of MOFs. And next one is the conventional preparation of the MOFs. Next one is the synthesis of the HKUST1 samples using room temperature and the solvothermal synthesis. And then we discuss about the results. And lastly, I will discuss about the application work, kinetics and the adsorption isotherms using MP dye adsorption on the HKUST1 sample. Last one is the conclusion. Firstly, introduction to the metal organic frameworks. As we name suggest, metal organics and organic linkers gives the formation of the metal organic frameworks. MOFs have the ultra high porosity up to 90% volumes. Next one is the various properties and application of MOFs. MOFs have the wide variety of applications due to their large surface area and porous natures and the strong bond between the metal ions and the organic linkers. Photodetectors, biosensors, supercapacitors, electrochemical sensors, photocatalysis, GaN sensors, wide varieties of applications. MOFs are semiconductors or insulators with a wide band gap range 1.0 electron volt and the 5.5 electron volt, which can be altered by changing the degree of conjugations in the ligands. Many conventional preparation methods, solvothermal, slow evaporation, mechanochemical, electrochemical, microwave synthesis, sonochemical synthesis, but most of the MOF synthesized by hydrothermal. So synthesis of the HKUST1 sample using room temperature and the solvothermal techniques. First one is the metal salt solution. This is Cu1 and the 75% ethanol volume ratio and magnetic stirrer for 1 hour. Next one is the linker salt solution and the 75% ethanol volume ratio and the magnetic stirrer. And the metal salt solution added dropwise into the linker salt solution and continuously magnetic stirrer. And the Cu based MOF precipitate are formed, then the sample was transferred to the centrifuge and then the sample was drying and then finally sample was synthesized. Next one is the solvothermal techniques. The process is same up to adding dropwise the solution. Then the solution was transferred into the autoclave. Then after cooling, then into the room temperature. Then the sample was transferred into the centrifuge. Then washing and then the final sample was synthesized. Next one is the optical properties of HKUST1 samples. The UV visible adsorption spectrum shows a broad peak 200 to 400 nanometers due to the pi-pi transition of the linker solutions and the visible range adsorption between the 500 nanometer. It is due to the Cu2 positive DD spin allowed transitions due to the and the band gap of the RT samples is 3.49. The band gap of the RT solution is the 3.49 electron volt and the ST sample is the 3.40 electron volt using Tox plot. Next one is the FTIR spectroscopy. The basic changes in the FTIR spectrum as shown in this table. Next one is the XRD. The XRD pattern was matched with the JCPDS file and the structure is FCC and the average crystalline size for RT is 17.151 nanometer. For ST is 19.24 nanometer. Next one is the FE-SFAM. In this figure A for the RT sample and figure B for the ST samples, revealing the irregular shaped particles ranging from the size from the nanometer to the micrometer range. The RT synthesized sample as shown in this figure A with a higher porosity with small irregular shaped layer sheets, and while the ST synthesized sample display a similar morphology but the reduced porosity and the larger layered sheet. Both sample poses and characteristic sponge-like structures with the particles are agglomerated in the connected network-like manners. Next one is the Raman spectroscopy. The low wavelength peaks at 224 and 2264 RT and ST. 450 to 700 centimeter inverse is due to CUO coordination and the linker bending modes. The small peaks at 274 for RT, 297 for ST is due to the vibrations in the OCUO bendings. The common peaks at 740, 823 near about 1000 is the aromatic CHOCO and the benching ring vibrations. RT shows a unique peak at 1289 centimeters due to the OH bending, and the ST shows the 1 to 14 centimeter inverse is the benzene vibrations. And the strong peak at 1603 centimeter inverse is the CCC stretching and the COO negative vibrations. Next one is the BET. The BET surface area for RT synthesized sample is 666.650 meters square per gram, and the ST sample was is half of the RT sample, which is 315.372 meters square per gram, and the Shobson isotherm as shown in this figure, and the inset shows the pore width distribution of the HCUST1 samples. Next one is the Zeta potential. Zeta potential done is the at neutral pH for RT. The Zeta potential values is minus 5.64 millivolt for RT and the minus 3.75 millivolt for ST. Negative surface charges promotes the electrostatic attractions, enhance adsorption of the positively charged MB molecules onto the catalyst. Next one is the application work, adsorption studies of MB on HCUST1 samples. We have done the RT and ST. We have two catalyst dose 0.25 gram per liter for the both sample RT and ST, and next one is the 0.5 gram per liter for RT and ST. In this experiment have done in the whole duration in dark conditions for 180 minutes. Next one is the according to the adsorption studies of MB, we have done the kinetic parameters and derived constant. We can find these we have follow in the RT pseudo second order is applied, and in the case of ST pseudo second order is applied in this figure 14 kinetics models. In the figure 15 it is the fitting of the intraparticle diffusion models on the adsorption curves of MB dye using HCUST1 RT at a catalyst dose of 0.25 gram per liter and 0.50 gram per liter for ST. Next one is the according to these parameters we can find the kinetics constant for the adsorption of the MB dye using HCUST1 RT and ST. We can find the table. Next one is the adsorption isotherms and derived constant for the adsorption of MB dye using HCUST1 sample. Figure 16a we have done the sample of RT and we have done the B sample for the ST. Fitting of the adsorption isotherms model for RT and ST at a catalyst dose of 0.50 gram per liter, and this table shows the constant isotherm constants for the adsorption of MB dye using RT and ST. And we have the Langmuir parameters also followed for the RT and the ST. And final next one is the conclusion. HCUST1 successfully synthesized via room temperature and the solvothermal methods, both sample comparative physiochemical properties confirming RT synthesis as a cost-effective alternative. Negative surface charge enhanced adsorption of the cationic MB dye. MB removal efficiency increased with the catalyst dose, reaching at a maximum of 55.95% at a 0.50 gram per liter for ST. Adsorption follows for the HCUST1 sample shows the pseudo second order follows, indicating the chemosorption involvement. Isotherm analysis fitted for HCUST1 sample shows the Langmuir model. It confirms the monolayer adsorption on the homogeneous surface, and the overall demonstrate it is used in the wastewater applications and the room temperature synthesis. HCUST1 is equally efficient, make it suitable for secondary and economical productions. Thank you.
Sir, can you go to your slide number 7? Figure 10. Absorption. Next, right? 11. Yeah. So can you able to explain the shape of this curve like that?
Sir, ये type 4 hysteresis curve.
Why did you decrease like that?
Sir, according to the literature, this type shape is type 4 hysteresis. Yes. Sir, due to porous nature.
पहले आप बढ़ा रहे हैं ना? If you are
Yes, sir.
increasing the pressure, then volume is increasing. Then it will attain the maximum.
Yes, sir.
Again it is decreasing.
Sorry, sir. Can't.
ऊपर वाले में जो है ना एरिया कम हो रहा है.
हाँ जी, sir.
What information that you can get out?
Sir, average pore width is for RT is 3.06 and the decrease in the, but it can increase in the pore width for ST samples. मतलब
Second one, last slide, Raman spectrum. So if I compare these two Raman spectrum, so then most of the peaks are not matching.
Sir, actually.
So for example, like there are peak around 1500 huge peak in there, 1640.
Yes,
so there are no peak in number one. So at first peak, there is no much.
Sir, some peaks are मतलब shifted, sir. Mostly peaks.
Peak intensity is also changing.
Thank you,
So
sir.
what is the reason? Just by changing some morphology, we are able to change.
Yes, sir. We can change the synthesis process. तो हम मतलब जो रमन स्पेक्ट्रोस्कोपी है इन सब चीज़ों में थोड़े थोड़े मतलब चेंजेस आते हैं इनमें.
Like between 400 and 600.
Yes, sir.
Clear peaks are there.
Yes, sir.
But on the red one, there is no any peak. So you have identified peak 4 and 4. But it is just like a background. Actually, up to 494, 507, 494. In red data, you have mentioned 494 and 507.
Yes, sir. Sir, according to the literature.
According to the literature.
Yes, sir.
You are not getting any peak, and what is the indication of that?
Sir, I forgot to.
Proper nice.
Do we have questions from the audience? You said you have used two methods. Can you go to your last slide? Conclusions. When you say that H+1 was successfully synthesized via room temperature and solvothermal methods. So solvothermal is a method.
Yes, sir.
But room temperature is a method? How do you call it like?
Ma'am, room temperature mostly जैसे we use the magnetic stirrer at room temperature, only magnetic stirrer.
So which method would you call it?
Ma'am, only room temperature.
Room temperature is the temperature at which you are synthesizing.
Co-precipitate method, ma'am.
Okay. With this, we thank you for your talk.
Thank you.
Thank you. The third oral presentation is by Dr. Roshan Josh. Do we have Dr. Roshan Josh here? He's from Department of Physics, Marian College, Kuttikanam, Kerala. His title of presentation is Investigation of the Current Voltage Behavior of ZnO2, ZrO2, EVA Composite Thin Films on ITU.
Okay. So I would like to thank Dr. Surendra Kumar for inviting me to give a talk. I was his batchmate. presently I am working. Okay, presently I am working in Marine College, Guttikanam, Idiki, Kerala, which is actually very far from here. So, because of his invitation only, I came here. So, my title of the talk is Effect of Tantalum Doping on Dielectric, Ferroelectric and Piezoelectric Properties of this particular compound SRBA4 TA4O15. So, this particular compound is belongs to a bismuth layer structured compound, which is having a bismuth oxide layer interleaved with a perovskite layers. So, based on the number of perovskite layers, we can have many number of possible compounds, which is also called as a Urey-Willis set of compounds. So, this perovskite layer can be composed of many combination of this any particular different oxidation state elements. So, we have chosen strontium as an A site and bismuth as a titanium as a B site. So, it will become SRBA4 TA4O15, which will be having a 4 layers of perovskite layer. So, this kind of compound shows a very good ferroelectric property and as well as a piezoelectric property. So, the advantage of this particular compound is which is having a lead free composition. So, if you consider one of the best material for ferroelectric or a piezoelectric application, which is based on lead based ceramics like lead zirconium titanate. So, lead, as you know, which is a cancer causing element. So, there is a need of eco-friendly compound which will replace the lead based compounds from the industry. And the second advantage of this particular bismuth layered compound is which is having a high phase transition temperature. So, which means below 590 degree, this compound will actually show the piezoelectric or ferroelectric property. So, when you consider the lead based compounds, which is actually having a transition temperature of around 250 degree. Then another key property of this particular compound is it will show the very stable electrical properties based on the temperature. So, this is again the crystal structure of this particular compound. So, the main source of ferroelectricity, it is due to the anisotropic crystal structure. So, which is because of the tilting of this particular titanium octahedra in this particular compound. So, if you want to change the properties, electrical properties of this particular compounds, one way to replace the titanium site with any other suitable elements. So, I have chosen tantalum as a doping element in place of this particular titanium. So, tantalum, as you know, that which is having an oxidation state of 5 plus compared with the titanium, it will act as a donor ion. So, again the motivation which is that if you synthesis this particular compound, if you want very high yield compounds, we will always go for high temperature synthesis, which is like a solid state synthesis. So, whenever you go for a high temperature synthesis, these compounds will always have a defects which is because of the volatilization of this particular bismuth ions, which will create oxygen vacancies, and this because of high temperature sintering, this normal oxygen also will become vacancies. And if you try to dope the tantalum in place of this titanium, which will give this extra 2 electron to the lattice, and this reduce this oxygen vacancies, and this keep this particular compound as a defect free, and it will give gives rise to good property, good electrical property. So, these are the 4 compounds we have synthesized by doping tantalum. We have adopted a solid state reaction for the sample preparation. Extra 5-8% of bismuth oxide we have added for compensating the evaporation loss. And first we have ball milled this particular carbon dioxides and oxides. Then we have go for a high temperature treatment, 950 degree for 3 hours. again we have made pellets using this particular powder, and by using this pellet again we have temperature treated for high temperature for getting dense samples. So these pellets were used for further electrical characterization and structural characterization. So these are the XRD patterns, undoped and doped samples. So we could obtain a single phase for all the compositions. But what we can observe is after getting the lattice parameters from the retooled refinement, we could observe a increase in lattice volume. So which might be because of the larger ionic radius of this tantalum compared with this particular titanium. And these are the microstructures. So this is undoped. So when you try to dope the tantalum, this particular length of the platelets which is reducing when we try to dope the tantalum. So these are the dielectric measurement. So if you can see that compared with the undoped one, that is a SBTA, labeled as SBTA. So when we dope tantalum, the dielectric constant will be increasing. So which is a good dielectric constant is obtained for a 0.3 percentage tantalum doping, and you can see the dielectric loss as well. The dielectric loss also decreased when we dope the tantalum in place of titanium. So these are the ferroelectric and piezoelectric measurement. So we could not observe any high improvement in ferroelectric and piezoelectric measurement. Very small remnant polarization as well as the piezoelectric coefficient improvement in after doping this particular tantalum. So we again go for a specific heat measurement for seeing the temperature stability of the samples. So we can see that after doping tantalum, the specific heat capacity which is decreasing compared with the undoped one. So which means that the temperature stability compared with the surrounding the tantalum doped samples can get easily heat up. So which is decreasing actually the temperature stability. So these are some of the second figure is zoomed portion of around 400 to 500 degree, so which is actually showing the phase transition. These are the conclusions. So we could conclude that a small percentage of tantalum doping could improve the properties of this particular SRBA4 of 15's performance, electrical performance. Thank you.
Thank you, Dr. Roshan. Do we have questions from the audience?
So why there is a change in the grain size just by small doping of tantalum?
Grain size, the oxygen vacancy might be reducing. That might be the reason, because actually this atomic doping. So you are asking for this, why there is a microstructure change. That's a question, no?
Yeah, because you mentioned grain size is changing. In conclusion also you mentioned that changing the grain size when you are doing the doping. So why grain size change?
Yeah.
And another thing is in your XRD data, if you can look into the difference curve, particularly like in second data.
Yes.
So from that refinement is not that good quality. Sample B.
Okay, 0.03. Okay.
Yeah, so
okay.
major peak of 30 degree that you can see.
Okay. That so different is yes, difference is
difference is there.
Okay.
So on the basis of that, how you can show like that?
Okay, I'll look into that, sir.
Okay. Thank you.
Okay.
Thank you, Dr. Josh. The fourth oral presentation is by Dr. Rakhi Kumari, Department of Physics and Astrophysics, DU. Her title of presentation is Statistical Physics Framework for Protein Families by a Random Mix and Network Theory.
नहीं हो जाएगा। वो बड़ा कर दो बीच वाला, ऊपर
कंट्रोल है
साइड, द मिडल वन।
PDF है ना मैम, maybe this is PDF. PDF you should provide presentation.
वो लेटेक वाली है ना, तो लेटेक में PDF है।
नहीं PDF को आप डाउनलोड करके कंट्रोल है तो रीच लेंगे।
PDF डाउनलोडेड है ना?
इसमें डबल क्लिक करिए।
So thank you, ma'am. So title of my talk is Statistical Physics Framework for Protein Families via Random Matrix and Network Theory. So here are the outlines of my talk. First of all, introduction towards random matrix theory and network analysis. So here I am using two tools, that are random matrix and network theory. Next is motivation and methodology behind my work. Third point is random matrix analysis for 7 protein families. So we have analyzed 7 protein families, and we do the analysis by using two approaches, random matrix, and the second one is the network approach. Fourth point is statistical analysis of protein families, then a network and random matrix approach. Then on the fifth we have one particular protein, that is IgPD protein, and we determine the structure sites by using the property based correlation matrices, then conclusion and some of the references. First of all, introduction. So introduction to random matrix theory. So the idea of random matrix theory was proposed by John Wishart in 1920. In 1920 he analyzed some statistical properties which are eigenvalues of random matrices. Then after John Wishart, E. Wigner discovered the Wigner surmise, which he used to study the distance between energy levels of heavy nuclei atoms. Then Freeman J. Dyson classified the random matrix ensembles according to their invariance, whether they are invariant under orthogonal transformation, unitary transformation. Then Madan Lal Mehta studied the link between the random matrices and the energy level theory. So random matrix, what is a random matrix? So random matrix is a matrix whose entries are taken from some random distribution. So here we are taking the entries from Gaussian distribution, in which we are taking mean 0 and variance unity. So these entries, the entries in the random matrix can be real or complex numbers. So they are extensively studied in the field of random matrix theory, which explores some statistical properties of random matrices and their applications. In the application part, random matrix can be used to model the complex systems which exhibit randomness, such as the electron in a metal, which are a very random system. And also the random matrix used to study the behavior of mathematical objects like eigenvectors and eigenvalues of the matrices. Next tool which we are using is the network theory. So introduction to network theory. So first idea of network theory was given by Euler in 1736. So Euler gave the mathematical description of vertices and edges. So what are the vertices and what are the edges? Then after Euler, Paul Ardos and Alfred Rennie developed the probabilistic theory. After these two scientists, Duncan Watts and Stephen Stogast, gave the empirical data on network and described the small world network. So Albert Laszlo Barabasi and Rekha Albert discovered the famous scale-free network, which captures the fact that real networks exhibit hubs that with many small degree vertices. So motivation and methodology. So as protein comprise of very long sequences which consist of amino acids and that fold and make a very complex structure. So to study these structures, the experimental techniques like nuclear magnetic resonance and the X-ray crystallography give some limited information about the specificity determining sites, which are known as SDS sites. So these studies, these experimental studies are very costly and take a lot of effort and take a lot of time. So we need some new computational method so that we can explore these functional and structural sites in the proteins by less effort and very cheap way. So we use this property based data, and in the methodology part we analyze proteins as a string of amino acids, and first we refine the proteins by eliminating the sequences which have similarity greater than 90%, and we eliminate the gaps which have greater than 20%. Then we calculate the correlation between these. So this is the data representation. On the left hand side we have multiple sequence alignment. This is the protein data in which there are 20 amino acids, and we replace these amino acids with their respective physiochemical properties like hydrophobicity, polarity and volume. So next thing we do the Wishart matrix and the Marchenko-Pasteur distribution. To do the Marchenko-Pasteur we calculate this spectral distribution of matrix, and we find out the lower and upper bound which are lambda plus and lambda minus. So the eigenvalues which are between the lambda plus and lambda minus are behaving like random, but the eigenvalues which are outside these bounds carry specific information about that protein family. So next tool which we are using is the inverse participation ratio and Shannon entropy. So inverse participation ratio gives us that the number of components that contribute significantly will have the amount of deviation from the random matrix prediction, and the Shannon entropy gives us the information content for those eigenvalues. And in the network analysis tool we calculate the correlation threshold, network and the network density by using these, that if we have I is not equal to j and the correlation is greater than some threshold, particular threshold, we have S between two nets, otherwise it is 0. So next important property is the clustering coefficient in the network. So clustering coefficient is a measure of density of the neighborhood of a node, means how a node is connected to the neighborhood of different nodes. So if the clustering coefficient is high, means that position is very important for the protein, means it is highly correlated with other positions. So in protein networks, the nodes which have high clustering indicates that the node is surrounded by positions with strong interactions among each other. So these neighborhoods are part of sectors that form the important regions in our protein family. So next is the random matrix, and so we have taken these 7 protein families. You can see that each protein family have different number of sequences with different length. So these are the 7 protein families which we studied. So this is the result part, means first we study the cadherin 4 protein, we find out the eigenvalue distribution. First plot, A plot, you can see that the eigenvalues are outside the random matrix part. In the insert you can see that the random matrix which are outside the random part, means these are highly important for that particular protein. Next protein is the IGPD protein. We have calculated the eigenvalue distribution, nearest neighbor and the number variance. Next is the comparison between cadherin 4 and beta lactamase. This is the heat map of these two proteins. Next we have calculated the inverse participation ratio and Shannon entropy for these two proteins, cadherin and the beta lactamase. And this is the square eigenvalue components. This is the network part for the beta lactamase family, and this is the network part for the cadherin 4 protein family. This is the degree distribution plot for different threshold for the cadherin as well as the beta lactamase. And this is the calculation for the network density and the clustering coefficient for the cadherin 4 and the beta lactamase. Next we focus on the other protein, which is the IGPD protein. We have calculated the inverse participation ratio and Shannon entropy. And this is the network part for the IGPD protein. And these are the important positions for this particular protein. And this is the PDB structure of the IgPD protein, and we locate these important positions on this PDB structure. And in the conclusion, we conclude that random matrix theory is very useful for predicting the signal from noise, and also network analysis approach is useful in protein families, structural and functional motifs. So we found that the important positions that matches with the experimental results also, and these positions are responsible for the structure and function of the protein. So these are the few of the references. These are the references. And thank you very much.
Thank you, Dr. Raki. The session is open for questions.
So I have gone through your reference. Most of your reference is quite old. So
Yes, sir.
So no one is working in this area?
Sir, working in this area, but the work I have done is means this is the 2016 paper.
So after 2016, from last 10 years, there is no paper in this area.
We working on this. We working in this field. So this will Pradeep Bhadola and Nivedita Dev is my supervisor. So this is the field of biophysics.
That's fine. From your group, you can also add as a reference. No? If there is any paper from your group.
In 2025 there is a paper. There are papers in the last few years as well, but in the references I have added the papers which
Second thing is that whatever result that you got, what is the authenticity of that? Like whether you compare with some other data?
Yeah, we have compared these with the experimental proof. Means these positions like 55, 77, 73, 77, 1 to 1 are found experimentally as well. Means these are the references which found these important positions by using the experimental techniques.
So how much is error? Like exactly matching same or some?
Means some of the positions we have predicted but not found experimental till now, but almost 80% positions found experimentally.
And another thing for protein, I think you have taken only 3 physiochemical parameter of protein.
Physiochemical properties, yeah. So
only 3 you have considered, but there are a number of properties are there. Like
there are very large number of properties, but we mainly focus on those properties which are highly important for that proteins. Means there are many properties, so we are mainly focused on like hydrophobicity, polarity, polarizability, and relative mutability. So we are using these 4 properties. So in literature, these 4 properties play a major role in the protein structure and function. That's why we are taking these 4 properties. We can take other as well.
I have a very naive question. When you were introducing this random matrix in the beginning, you said that you get some random input, but you took Gaussian as an example.
Gaussian as an example, yes.
But Gaussian, I would describe it as a probability-specific distribution.
Yes.
It is not random as far as I'm not from this field. So I was having this query when you introduced random matrix in the very beginning. You used Gaussian as if Gaussian is something very random. But according to me, it has a specific probability distribution.
Yeah, it has specific probability distribution, but it behaves like random. Means when we are taking as an ensemble, means very large number of data, then the Gaussian orthogonal ensembles is behaving like some random thing.
It's fine. I'm just wondering why are you calling it random? For me, Gaussian has a maxima.
Yeah, Gaussian has a maxima and the tails as well. But when we are talking about the ensembles, means we are taking a very large number of data, because proteins are made up of very large number of sequences, like 50,000 or 1 lakh number of sequences. So that's why it is.
Okay, thank you.
Thank you, sir.
Thank you, Dr. Raki. So with this, we come to the end of today's session. We thank all the presenters and the audience as well. Thank you so much.
I would also like to express our sincere gratitude I would also like to express our sincere gratitude to our respected chairperson, Professor K. Srivastav, for successfully chairing this session, technical session 2. We will now take a short break for tea. Tea will be served at the Samarth Guru Ram Das Auditorium on ground floor. We will resume the session 3 after 10 to 15 minutes. Kindly be present in the auditorium on time.
इसको फर्स्ट वाले डिटर्मिन में ले आओ।
evening everyone. We now proceed with session 3 of the conference. Before we proceed further, it is my pleasure to introduce Professor Manish Kumar Kashyap. Professor Manish K. Kashyap is currently a professor of physics at the School of Physical Sciences at Jawaharlal Nehru University, New Delhi. He previously served at Kurukshetra University as assistant and associate professor and also at Government College, Narayangarh. He completed his PhD from IIT Roorkee and pursued postdoctoral research at Amy's Laboratory, USA, under the UGC Raman Fellowship. A two-time gold medalist in BSc and MSc Physics, he has consistently demonstrated academic excellence. His research lies in theoretical condensed matter physics, material science and plasma physics, with a focus on 2D materials, perovskite solar cells, sprintonics and DFT simulations. Professor Kashyap has published over 110 research papers and has guided 9 PhD scholars with several currently under his supervision. He has completed multiple research projects funded by UGC and DST and continues to contribute actively to academia and research. For this session, I am honored to have Dr. Manish Kashyap from JNU Delhi as our session chair. Now, I request RTIC Dr. to felicitate Professor Manish Kashyap by presenting him a shawl. Please give a big round of applause. I request to please come forward on the stage Dr. Shiv Shankar Gore and Professor Kashyap. Please give a big round of applause.
So now space is mine?
Yes. Now I kindly invite Dr. Manish Kashyap to take the chair.
Welcome to the post-P session, and in this session we have one invited talk and several oral presentation depending upon how many participants will be here. Okay, so let us focus on first talk first, and we have with us Dr. Updesh Verma from Department of Physics and Astrophysics, University of Delhi, and let me read his brief biodata. He is a researcher in surface and interface studies and electronic structure analysis using XPS and XAS. He has held a research position in France and Germany. He is a is your guy? Okay. Whatever has been given to me, so I was reading this one only. He's a very fast friend for me, and let us invite him to present the talk on the very specific topic, that is on ITER.
It changes. So good evening to all. Myself, Dr. Updesh Verma, as Professor Manish ji has already told. I am teaching physics at Department of Physics and Astrophysics at University of Delhi. So, because this conference is basically this conference is basically basically related to material science. So as I am working on energy, so I have just related my topic with these things, because plasma is a source of energy. It's a source of नहीं नहीं ठीक है हाँ it's a source of everlasting energy. So also it's called the fourth state of matter. So here we are like dealing with lot of material science. So this is also a fourth state of matter. So by which we are going to extract the energy, and this energy will be sustainable energy and will be the clean energy. And by which process we can get it? By the process of fusion. So Stephen Hawking also tells, like, quoted, I would like nuclear fusion to become a practical power source. It would provide an inexhaustible supply of energy without pollution or global warming. So why we are interested in fusion? Because here you can see this is an abundant fuel. Like recently you have heard a news, Prime Minister Modi has stated, like India has got the criticality in the breeder reactor technology, and it's like about many years of our hard work. So in that what happened, like we can use thorium in that breeder reactor, and thorium is very much abundant in India, like 25% of thorium of the world is in India. So that's why it is this fusion technology is very important. So first it is abundant fuel, and this is a clean energy. There are two processes, fission and fusion. In fission you will get the large nuclei, and it will break into the two smaller nuclei, and you will get the energy. That is called the fission. What happened in fusion? You have to have like two smaller nuclei, will fuse them and will get the more energy than the fission. So, and in that there is no like harmful or maybe any toxic things which is the byproduct. So that is called the clean energy, and safety is important. Also it has a high energy density. So that's why we are using the fusion. It has like sustainable global properties like energy security, climate mitigation, and also economic growth, because lot of jobs will be created when fusion will be there. There were some challenges, or we can say the hurdle in fusions, like some technical hurdles, like how we can like create that much of device which will sustain that amount of energy. And what type of amount of energy? Like the amount of temperature which will be in the core of sun, that temperature we can create in the lab. So that amount of temperature, how we can sustain it, how we can like tap it in a device, that is a hurdle. High initial cost. So the project we will talking about will be the highest paid in terms of money, like $20 billion euros will be the cost of that project. Public perception is like if there is a nuclear thing, then it will be dangerous. So that is not the thing. What we will get? We will get the international collaborations, renewable energy integration. This is the long-term vision. Like our Prime Minister has tweeted, like we have got the criticality, but it takes like more than 40 years. So it's a long-term vision. So now we will see like the medium we are talking, the fourth state of matter, that is called the plasma. So what is plasma? So basically in general perception we say that it is the fourth state of matter. First is solid, then if we put the energy in solid, it will become the liquid. If we put more energy or we increase the temperature of the solid, it will become the liquid. Then liquid और उसे energy देंगे, it will become the gas. So that is the third phase. But if we put more energy to the gas, then it will create the plasma, but with certain conditions. So what will be that condition? Or also we find that plasma is a fourth state of matter. It's like okay, and it's a perception that it's really found in surroundings, but it's a wrong perception because 99% of the universe is our plasma. So like in this graph we have shown like if we put a temperature in the solid, it will become liquid. Then if we put more energy into the liquid, it will become gas, and finally it will become the plasma. But what about the exact definition of plasma? So from here we can see, from here we can see that plasma is called the quasi-neutral ionized gas. That is, this is not 100% neutral. There will be like 99.9% neutral. So that is called the plasma, and it depends on the three properties like particle density, particle temperature, and magnetic field. If we know all these quantities, then we can characterize the plasma. These are like ordinary gas in which atoms are little bit farther. If we put energy inside it, it will become the gas. What happens like in atoms, the electron will strip out. So there will be atoms, neutral atoms, ions, as well as positive and negative ions. So that positive and negative ion is called the plasma thing. There are some examples of plasma like you can see in the universe. Eagle Nebula, these all are made up of plasma. These are giant structures in space. This is your Cygnus Nebula. This is also we can see by observatories. Our sun, this is an important part of lot of energy. These are the aurora in Alaska, in which we will have the lights, colorful lights. Neon tubes. These are the common sources of plasmas. Rocket thrusters. There are a lot of research going on the thrusters, like what kind of thrusters we can do research so that it will become more efficient. These are some of the like applications of the plasma, like lightning displays, natural phenomena, semiconductor, industrial technology, semiconductor manufacturing, surface treatment, wastewater management, like that. Also, like there nowadays work is going on plasma seeding. Like if you pass the seeds from the plasma environment, so what happens like the shelf life of the seeds will increase. Also, if the food we can process with the plasma, it will increase the shelf life of food. Like if the food get contaminated in 2 days, but if we pass through the plasma medium, it will be like 15 or maybe 1 month or more than that. So plasma is very important for that purpose. So these are the basic things in plasma. So I have shown you like the plasma is not a neutral. This is a quasi-neutral. That means 99.9% neutral. So where the non-neutrality shows, this is called the Debye shielding. Like if we put there is a positive negative charges. If we put some positive charges inside that, then there will be some sphere. Like जो positive charge होगा उसके चारों तरफ क्या होगा, negative charge इकट्ठे हो जाएंगे. So that is become the sphere, and this sphere is called the Debye sphere, and the radius of that sphere is called the Debye length. So in that Debye length there is no neutrality condition. So that's why this plasma is called the quasi-neutral. So these are the three conditions if a gas become the plasma. Like the Debye length should be greater than the length of the plasma, like in which we are putting the plasma, the chamber, that length should be greater than the Debye length. The number density, like this Debye length in which the number density, that means that should be greater than 1, so that there will be proper shielding. And third, omega, p and tau, like this is the frequency and tau is the time period, it should be greater than 1. Now there are
frontier areas of research in plasma, there are a lot of things like terahertz radiation generation we can study in plasma, electron acceleration, proton acceleration, parametric instabilities, harmonic generation, space exploration, and finally the thing what we are going to discuss here, this is called the ITR, that is called the International Thermonuclear Experimental Reactor. I have made this talk very simple, not any technical things will be there, just for simple you people. So these are the things which we have covered, like electron acceleration, radio communication, medical application. You will see lot of things, like you will see in the airports there will be like big machines by which you have to pass your baggages, but that is called the X-rays. But now we are using the terahertz because X-rays are little bit harmful for the human being. So these terahertz we can generate from the plasma. So by these things we can detect if a person is hiding some weapons. So we can detect easily by these terahertz radiations. Cosmological study of star, and so there are in the device which we are going to talk, that is called the tokamak, and there are two type of technique which nowadays people are researching. First is called the ICF, that is called the inertial confinement fusion, and second one is called the MCF, magnetic confinement fusion. So there is a laboratory called NIF, National Ignition Facility at the United States of America, in which this first one ICF, inertial confinement fusion technique, by this technique fusion is generated. So these are the like 96 small beams, and it is colliding on a small hohlraum. So by hohlraum what we mean, if you see the pupil of your eye, so this much of the size of that hohlraum, and ये जो 96 beams है, these are focusing on that hohlraum, and in that hohlraum deuterium tritium fuel will be there, and that beams will fuse that deuterium and tritium and will create the fusion energy. And the second method is called the magnetic confinement fusion, that is called the MCF. Like I have already told why there is a need of fusion, like there is a energy demand, energy, this on the y-axis there is a energy consumption in billion of barrels of fuel, and on the x-axis there is a years. So this red line shows, red and blue line shows there is shortfall of energy. So this much of energy we have to create, but how we can create this energy? So that cannot be created by fossil fuels, not even other sources. Only fusion energy will be there which can be used to bridge this energy gap. And what about the energy needs of India? Like this graph shows where is India. India is here in the first one part, and in United States and other developing countries these are on the top. Like life expectancy at America, Japan, Switzerland, there is like 80 years, but here where India lies, it is less than 60 years. And if we have more energy, then we can like extend this gap from 60 to maybe more than that. So that's why we need the energy. These are some of the facts why like energy needs of India. Like presently per capita energy consumption कितना है? 500 kilowatts per hour, which is very small, which is only about 1/2 part of China, 1/4 of the world average, and about 1/13 of the developed nation. So now India aspires to reach at least the global average by 2050, and it requires her to produce 1300 gigawatts of electricity. That means presently we are generating 130 gigawatts. So we have to gave it like 10 times more than that. So these are the some of the facts. There are some important facts which we can, these are the very recent one. Okay, what is going on in this fusion energy in 2026? So here you can see like Google announces world largest AI and data center hub in Visakhapatnam. But you know, to have AI, what we have to have data centers, and that data centers run by energy. So that energy, from where that energy comes? That energy will come from the fusion energy. Otherwise, fossil fuel will deplete very soon. So that clean and alternate fossil fuel energy will be the fusion energy. These are some of the news, recent news which we are having nowadays. This we have shown like how much energy demand of India is going for nuclear. This is like 64.50 now, because Indian Prime Minister has already told like in 2070 we will get the net neutrality, net zero neutrality. That means कि जो main total carbon emission है, that will not be zero, but we will, whatever the carbon we are producing, we will balance it. So that is called the net neutrality. Here we can see like solar power 110.9, biopower 11.6, small hydropowers, wind power, nuclear 8.8. So nuclear is only 8.0. So there is a lot of gap in it, lot of opportunities in it. Recently, in Union Budget of 25-26 has like Indian government has created lot of scope for this small industries and as well as these nuclear industries. This is called the Shanti Bill. You can see on the Google. These are the some of the energy reactions which are taking place in sun, and that sun energy we want to create at the laboratory. These are the main the things. So basically the machine which we are talking about is called the tokamak, and tokamak is the Russian word. Tokamak means the device in which we can contain something. Previously there was tokamak as well as sterilizer. Sterilizer was also machine to have the fusion, but it is now abundant, and like some prototype is in PPPL, that is called the Princeton Plasma Physics Laboratory, from where I have done my postdoc. So it was like a covered में रखा हुआ है as a prototype. So these are the demo reactors like JT60 in Japan, ITER in France, and the demo reactor. This will complete in 2040, expected to complete in 2040, and this is the demo means demonstrator reactor. Okay, if we can make this demonstrative reactor, then all the energy crisis of world will be solved. So what will be the solution for fusion energy? That is called the ITER. ITER is International Thermonuclear Experimental Reactor. So you can see the size of this machine. The man is on the floor, and this like more than 12-storied building. So this is a very huge machine, and costing is 20 billion euros around. So this is the plasma, like you can see, this is a pictorial representation, like how you can see like what is the plasma inside the tokamak. And this is the actual figure of K-star tokamak. But there are certain challenges, like whatever the things, like if this is a table, if we increase the temperature of the table for like 100 or maybe 110 degrees centigrade, it will burn out. But also like for concrete, there is certain temperature, after that it will be burn out. But plasma is that medium where there is no damage threshold, like it can contain any type, any amount of temperature, like that it can also contain the temperature of the sun. So that's why we are using plasma. We are generating plasma inside that device, that is called the ITR, and we will have the fusion energy inside it, and then we can get the energy out of that device. So basic fuel is DT fuel, deuterium and tritium fuel. Because of the shortage of time, will is not going into the details of that. So ITER means the way in Latin. It's an experimental fusion reactor being constructed presently at Cadrache in south of France. What will be producing, like in tokamak, in any machine, there will be some factors, like if we putting energy inside it and what the output is we are expecting, so that is called the Q factor. So if the Q factor, so here in this ITR we will get the Q factor greater than 10. So if we, that means if we are putting one some amount of energy, and that will produce the 10 times of that energy, that ITR. This is the basic figures of the plant, the plot where this machine is being created, and now it is like this one because all the construction has already done. This is the plasma, the purple one, in which this ITER tokamak. The seven, basically the 7 countries, China, European Union, India, Japan, Korea, Russia and United States. These are participating, but Europe has lot of countries, so total number of countries will be 35. These are some of the timelines of this ITR, like it starts in 2005. And now first plasma was expected in December 2025, but due to some conditions it delays, and DT operation begins in 2035. These are some of the timelines of this project. And the cost is increasing day by day. Previously it was like 20 billions, now at 22 billions. So this is the most costly experiment in this world. And this is the recent figure, 23rd February 2026, where the central part of the ITER is being installed. So objective is very clear. We have to generate the energy from this device, and finally we'll get the demonstration reactor, from which we will extract the energy through the like electricity, like in electricity. These are the some scales you can see, like if you are having 2 lakhs of tons of this coal, and for fusion only 1 car, that much of material is required. So you can see like there is a lot of difference. There are a lot of things in this ITER, like the total weight is 23,000 tons, and one Eiffel Tower is 7,300 tons. Like that means 3 times more than Eiffel Tower. This machine is weighted. This is a inner chamber of that machine, and it is 840 cubic meters. So like when you purchase a car, you will see like there is a 1.5 liter car engine. So that is the inner chamber in which the reactions will take place, and you can see like 840 cubic meters. It's a huge size. More than 5,000 workers per day are working in it, or more than 50,000 have already visited that site. Because the size of the some of the elements are very big, so we have to create a special roads for that. So more than 104 kilometers special road is created for that eater. This is the pit of that device, and it is like 3,60,000 tons of the material is put inside this pit to construct the base of that device. These are the visitors. Also you can see like each there are like 18 D shaped of just finishing. There are 18 D shaped of elements are included to make this inner chamber, and each D shaped is having weight of 360 ton, and which is the weight of one Boeing aircraft. So you can see the weight of that thing also. This we have already completed. So just to show these things is to realize you like how big this project is. So these are the some. So now its present is cost is 30 billion euros. It has increased. And what India is contributing? India is contributing, like every country is contributing 10% of thing in kind or maybe in cash. So these are some of the units. These are the previous data. Now it's become like 22 billions. So what we have here in India, we have this Aditya Tokamak, which is being built in IPR, that is Institute of Plasma Research in ITR. So what we are making here, we are putting it into the this ITR thing. So thank you very much for your attention.
Scientists in the future, and scientists will come from your side, that is the students. Any question now? Okay, I think no question. So can you tell the students, because I can see some of the students here, you might be in the BSc. So what are the opportunities for the BSc student, that how they can participate in this teacher program, maybe through internship, maybe through some visiting fellow?
Yes. So, like you can visit, if you want to learn internship in India, then you can visit ITER India website, or maybe simple. There are lot of internship opportunities for students. So you can visit that website iter.org. So regularly they post the requirements, whatever. Even you can visit there. So for students, they will provide some to and fro fare and lodging, boarding things. So you can visit the website regularly.
Okay, so let's thank the speaker now.
Thank you.
Now, I would also like to invite the chairperson, Dr. Manish Kashyap sir, to felicitate Dr. Uptesh Verma sir with a token of appreciation by presenting him a memento, a port and a certificate.
So ma'am will give to you. One more please. The token of love from Shivaji College.
Okay, let us proceed further for the oral presentation. So we have first oral presentation by Dr. Shrikala, and she is from Hansraj College, Delhi University. Her title of presentation is Spectroscopic Study on Frustrated Nickel Dope Spinal Oxide GeCO2O4. Please. So you have in total 10 minutes with discussion.
Okay, good evening everyone. I'll be discussing the results about spinel oxide material that we tried to investigate recently, that is germanium cobalt oxide with nickel doping. We have done some spectroscopic studies. This is the outline of my presentation. Along with the introduction, I'll briefly explain about the motivation of choosing this material, and I'll discuss some of the results. To begin with, spinel oxide is a part of family called spinel compound, whose formula is represented as AB2X4. X can be any of the chalcogen anion. Since we have taken oxygen, so it became spinel oxide. One can see the oxidation states. Based upon the oxidation states, we can classify them as 2,3 spinels or 4,2 spinels. In general, most of the times the crystal structure is cubic, and based on the occupation of the A and B atoms at various sites, we can further classify them as normal spinel, inverse spinel, and mixed spinel. In case of normal spinel, A atoms occupy tetrahedral site, B atom occupies the octahedral. That's a very normal spinel oxide. In case of inverse, the word itself says A actually occupies some of the octahedral sites, but B comes into tetrahedral as well as octahedral positions. Mixed, as the word says, that both A and B atoms occupy tetrahedron and octahedron. This is a schematic representation of the crystal structure. We can see a tetrahedron, the cornermost picture, with A atom, and the second one is an octahedron with a B atom. The sample that we choose to study is germanium cobalt oxide. Obviously, germanium is A atom, which occupies the tetrahedron GeO4, and cobalt, in place of that, we doped nickel. So these atoms occupy the octahedron, that is COO6. These are the crystal structures, just to give you an impression about how they occupy different sites. Mixed spinel is one thing that I would like to emphasize, where you see both the metallic cations occupying the tetrahedral as well as octahedral sites. This sample that we have chosen is very interesting because of its inherent magnetic frustration behavior. What you can see in figure B is a layered structure of cagome and triangular lattice planes, and this is for cobalt spins. We can place any of the magnetic atoms in that place. What you can see clearly here is in the first set, you can see the cobalt spins are aligned parallel. In the immediate set, you can see that they are also parallelly aligned, but when I compare the first and second layers, they are anti-parallelly arranged. So the reason behind the magnetic frustration in this sample is you see an interlayer antiferromagnetic exchange coupling along with in-plane ferromagnetic exchange coupling. So there is always a dominance between these two behaviors, and that's the reason the crystal becomes magnetically frustrated. We have used a simple solid state technique to prepare our samples. Oxides were used as precursors. The initial calcination was done at 1000 degrees centigrade for 18 hours, followed by sintering at the same temperature and for the same time. This is the XRD result, and the refinement was done with germanium considering at A site because that is what we expected. All the samples must exhibit a normal spinel crystal structure. But whereas when it comes to the last sample, that is germanium nickel oxide, we could do the refinement only by considering germanium both at A and B sites. The reason behind it, the sample was prepared at 1000 degrees, but there were some impurity phases, so we had to reheat it at 1200 degrees centigrade. So that's the reason this compound, this specific sample ended up in a mixed phase. These are the refinement parameters. Nickel is considered to be a smaller ion when compared to cobalt. So what we generally expect is the unit cell volume gets reduced, and that is what is been reflected in the cell parameters and the bond length. Of course, the last data point is between nickel and oxygen. Okay, and this is the crystallite size, which is very obvious that since nickel is small, the crystallite size has come down. And the table shows the atomic positions and the occupancy that we have calculated from the refinement process. So the last row is about germanium nickel oxide, where we can see both germanium and nickel atoms occupying tetrahedral as well as octahedral sites. These are the that's the reason I said that it is exhibiting a mixed spinel structure. Rest of the samples were showing a normal spinel structure. These are FSM pictures, and images source software was used to calculate the particle size. The particle size was between 110 to 200 nanometers. I haven't put the IDAC studies. We have done the IDAC studies as well. To confirm the atomic and weight percentage of all the elements that we have used to prepare this compound. We have done the UV studies to find out the energy band gap. The picture B shows the variation in the energy band gap, and the inset of it shows the function as a function of energy. So before the absorption edge, we could see 4 absorption bands at various energies. And what we also can see from that picture is a blue shift. Okay, since the crystallite size has decreased, so what we can simply understand is now the electrons are more strongly bound to the nucleus, so they need more energy to move from the valence band to the conduction band. So that is what we could see in the calculations of band gap. We wanted to ensure that it shows a direct band gap, so we have done that fitting also. And n value, the exponent value, is found out to be around 0.5 for all the samples, so we can confirm it that it has a direct band gap. We have also done the TGS studies, but we could do only till 1000 degrees centigrade only, and in all the samples we couldn't see any strong peak which shows the decomposition of the precursors that we have used in our sample preparation, and the weight loss percentage is almost negligible. So we can say that the structure or the samples that are prepared are much more stable. We have also done a few other studies like Raman, FTR, and we have also done some dielectric measurements till 10 Kelvin. I haven't shown that result. Coming to the conclusion of the presentation, we tried to prepare the germanium cobalt oxide spinel oxide series with nickel doping, and because of reheating process, we ended up with a mixed spinel oxide for germanium nickel oxide. But we have prepared the same sample at 1200, and that turned out to be a normal spinel. And the band gap is varying from 3 electron volts to 4 electron volts. We have done FTIR studies also. We have done the Raman experiment at room temperature till 77 Kelvin. And even our Raman studies exhibited that the doping of nickel has really caused the rotational and the vibrational phonon modes to be affected because of the ionic radius of nucleus. Our next process is to do the magnetization measurements. We have done the neutron at room temperature, but we are yet to do the low temperature measurements. And if possible, we'll also try to do the specific heat measurements. I would like to acknowledge the financial support that we received from UGCDA ECSR. And I thank Murugal sir from University of Delhi for providing me access to make samples in his lab. I thank Kaushik sir for XRD and refinement analysis, and I'm very thankful to USIC, University of Delhi, for providing the experimental apparatus to do the characterization. Thank you so much. Yes, sir.
You have made a particular materials in which you are trying to optimize the concentration of CO and Ni. Am I right?
Yeah, not yeah. Yeah.
Okay, so you are taking the fraction of Ni and CO, na?
Yeah.
So are you trying to optimize the concentration of CO and Mi for composition of CO?
No,
Or
sir.
you are taking random?
Uh, no, it's not about optimization. Our interest is to study the magnetic frustration behavior. How does it get affected if I dope nickel in place of cobalt, because nickel is a smaller ionic radii element. So that is the intention of doping.
Are you doing the doping within the solubility limit?
Yes, yes,
What is
yes.
that limit?
I don't know, but it is. We can make it. We could make it.
Okay, means same phase is there.
Yeah, yeah. It's the same phase.
One question for the U visible.
Yeah.
Okay, so see here the third one. But where is your baseline? So baseline is not starting from zero. Don't you think that you will have some deviation in the band gap? The baseline. It is not starting
From zero, huh?
It's not starting from zero.
Yes, sir.
Don't you think that if you start from zero, your red line will cut somewhere else?
Sir, I have done that also, but it didn't. Yeah, I didn't find any difference. I didn't find any difference.
Can be seen here.
No.
See here, so if you just take a horizontal line from zero,
Yeah.
then your red line will cut somewhere else. So your band gap may slightly increase. You can just check. Because we will discuss later. Huh?
Okay, I have done that also because
So baseline is very important. That's what I
yeah.
want to justify it.
Yeah, it ideally speaking, it should start from zero to some x value, just to ensure that we are hitting at the right x position, x value, right? Right value of
Even
energy.
if you are showing this one,
Yeah.
then you can take one more line
From the base.
Yes, yes, from the base.
And just to show the intersection point and say the exact value. Yeah, I'll do that. Thank you, sir.
Okay, so thank you for this presentation. Now the second oral presentation is by Dr. Harsh Yadav. Okay, so the third one is Dr. Dishu Daura, Ramjas College DU. The title of presentation will be Effect of Magnetic Field on the Atomic Properties of Ions Embedded in Dense Plasmas. Okay.
decreasing with the increase in nuclear charge also. Afterwards, this is a graph portraying the variation of plasma energy shift with respect to my electron density. So you can easily see that our plasma energy shift for this particular transition, that is defined here as 2s 2p singlet p1 odd to 2s 2 singlet s0 transition of beryllium like silicon, calcium and iron ions is increasing with increasing plasma densities, and moreover this effect becomes relatively less important for a given free electron density with increasing nuclear charge. So basically plasma screening will be decreasing with increasing nuclear charge. So now this is again the graph, but of course it will be portraying on the different type of a transition. Here I have studied the transition 2s 3p singlet p1 odd to 2s 2 singlet s0 transition, and it can be easily observed from the figure that the plasma energy shift for this particular transition is coming out to be 4.67 and 1.07 electron volts for beryllium like silicon and iron ions at a given electron density of 5 into 10 raised power 23 per centimeter cube. And moreover, since we have compared the energy shift for the other type of transition also, so we have observed that the energy shift is more pronounced for higher lying state as compared to our lower lying state, that is 2s 2p singlet p1 odd. Afterwards, we have also shown here the variation in the weighted oscillator strength GF for the resonance transitions as a function of free electron density, again for the particular ions that are silicon, calcium and iron ions. These three type of ions are beryllium like ions. So here we can easily see that the weighted oscillator strengths are increasing with increasing densities for the transitions 2s2 to 2s2p, whereas it is decreasing with increase in electron density for the transitions 2s2 to 2s3p. So basically the first type of transitions are delta n is equals to 0 transitions, and the second type of transitions are delta n not equal to 0. And after that, I have shown the variation of pressure on the ground state of beryllium like calcium ion with ion sphere radius r. So it can be easily seen that when we increase the ion sphere radius, so the enough space is there, electrons are less confined, so the pressure will be less. As soon as we decrease our ion sphere radius, so of course the space will be squeezed, electrons are more confined and the pressure will be large because the kinetic energy will be more then. After that, the influence of magnetic field on the spectral properties of highly charged ions is also studied there. So where we can write a total relativistic Hamiltonian, the first two terms are exactly the same which we have previously discussed, but the third term is again different, that is the Hamiltonian due to the magnetic field presence, and the last term, that is HB, is denoted by these two terms. So first term and the second term, they are corresponding to the linear and diamagnetic Zeeman term respectively, and these parameters A, R, S, L and B represent the position vector, spin angular momentum, orbital angular momentum and the magnetic field strength. So these are the graphs showing the Zeeman splitted energies of the excited states 2s 2p and 2s 3p. The states are triplet p1 odd and the singlet p1 odd states of beryllium like chromium ion as a function of magnetic field at different plasma parameters. So different plasma parameters have been labeled in the figure, showing this Ne to be 10 raised power 23 per centimeter cube and temperature ranging from 400 to 1200 electron volts with the parameter kept B to be 2. So here we can easily see that each level, because in the absence of magnetic field, that is basically when B is equal to 0, so each there will be one level corresponding to one excited state, but as soon as in the presence of magnetic field is applied, so each level will be splitted into 2j plus 1 mj levels. So lastly, I have shown here the variation of transition probabilities for the transitions, that is particularly focusing on the different mj values, 2s2 singlet s0 with mj is equals to 0 to 2s2p triplet p1 odd with mj to be 0 plus minus 1 of beryllium like again chromium ion with the magnetic field at different plasma parameters. So of course due to difference between due to difference of the dipole matrix element, these graphs can be understood. So lastly, I will be concluding my talk by saying that atomic data such as energy levels, radiative decay rates and oscillator strengths are essential for the modeling and diagnostics of astrophysical and laboratory plasmas, and including magnetic field and of course the plasma spinning effects enables accurate interpretation of spectral lines and reliable diagnostics of plasma temperature, density and the magnetic field strength. And moreover, these studies will also be providing the crucial atomic data for future fusion devices like ITR, supporting the development of practical fusion burning plasmas. These are the particularly references. So thank you very much for giving me this opportunity.
Thank you. Any questions?
that was the 1 electron Hamiltonian, which I have written basically for I equal to 1. I equal to 1. Because if we consider the many electron systems, of course the different will be, the Hamiltonian will be written according to the central field approximation. So that electron was 1 electron Hamiltonian. Yeah, of course. So basically Hamiltonian is the kinetic energy and our potential energy. So we are writing it in terms of a 1 electron, or we can also expand our Hamiltonian in terms of many electrons also. जैसे कि हम basically we firstly study the system of hydrogen atom, then move to helium, and then if we consider the many electron system like lithium, beryllium, so of course different approximations can be taken for writing our Hamiltonian. We are focusing on highly charged ions. So I am talking about the atomic structure parameters of highly charged ions. So I am talking about atoms or ions, depending upon how many electrons are extracted from there. Take it.
Okay.
One question from Jay.
Okay, so you have on the x-axis there is a magnetic field of this is 2 lakhs.
Yeah, 20,000 Teslas.
20,000 Teslas. So this much of magnetic field, where you have like taken the data?
So basically we have we assume that these type of magnetic fields, they occur in astrophysical objects like stars. So accordingly we are taking that strengths of the magnetic field. So basically we are giving a theoretical data as soon as we some experiments will be performed on these barium like chromium ions. So we will be able to compare our data, of course, with the pre-existing data. Yeah, of course it's a very high magnetic field. Yeah, these types of magnetic field can be existing in astrophysical objects. Yeah, of course. Yeah. There can be proper references that can be referred according to the strength of high magnetic field.
Thank you.
Thank you, everyone.
With this, we come to the end of the session 3. I would like to extend our heartfelt gratitude to our respected chairperson of this session, Dr. Manish Kashyap, for his guidance and for smoothly conducting this session. Again, thank you, sir, for successfully chairing this session. Now, I would also like to sincerely thank all our speakers for their insightful presentations and valuable contributions, which make this session truly enriching. Tomorrow we will proceed further with the invited talks and oral presentations according to the provided schedule in the same auditorium. Hope to see you all tomorrow. Thank you all.